All right, folks, welcome back. This is a beautiful morning in California. We are having sunshine after a long time, isn't it? And today is Saturday. Isn't today the April Fool's Day? Right?
Yes,
So
it
it's time
is.
for me to play a lot of pranks on you guys. All right. Let us recap what we have learned so far. We started out with a case study. We said, and the point of the first case study was, what is the value that natural language processing, the AI version of it, not just linguistic shredding of documents, but natural language processing, what value does it bring to a lot of common things we do? Now, search was something we have been doing for a long time. Linguistic search, keyword-based search has been around. Very mature engines are there. Apache Lucene is an absolutely awesome library, very mature with lots of features and bells and whistles. On top of Apache Lucene, for example, there is the Apache Solar, and then there is the Elasticsearch. Both of these are industrial strength, very heavily used search engines. They search through enterprise document at quite a large scale. And people create entire clusters of Solar. And
I'm going to Albert, could you please mute person?
Oh, sure.
No, it's all right. So people create massive deployments. These search engines are run on large clusters. But at the heart of it, the core idea remains the same. Though it goes through a lot of enhancements. The core idea is you take a document, find all the important words in it, the keywords. Then you create a sort of a dictionary list. A key is the key of a dictionary, or that hash table or hash map, is the word itself, the keyword itself. And the value is a list of those documents that contain this keyword. And people augment it, of course, not just by storing the document, but how often it was in the document or how relevant it was in the document, and many things. You can go and extend the idea further, but that's the basic concept. If you can keep what is called the inverted index of a keyword and all the documents that contain the keyword, the basic idea remains the same at heart. If you can create an inverted index from, given a keyword, what are all the documents that contain it, you have the germ idea or the kernel of all linguistic or keyword-based search engines. The problem with this, obviously, is that it is so different from the way you and I search. When we ask a friend for things, I joke that sometimes in my absent-mindedness, my wife says that, where is it kept? It is right there, you just go and then turn left and it is there, right? So the thing is, unless you're very contextually aware, go where and turn left where, right? So, and yet that's how we talk. So it is the context that tells us what is meant by a certain thing. We don't do keyword search, like we don't label all the locations in our house by certain keywords. In corporate world, we do that. Every room has a name, and we'll say, look in this conference room or discussion room. On the table of this discussion room, you'll find something, right? At home, it's much more amorphous, right? So that's sort of where AI search comes in. What if you could capture not the keywords, not force the user to bend and adapt to the technology, but have the technology infer what the user is trying to say in a very natural way, in a way human beings are used to speaking about or searching for things. Then that is AI search. You say that you understand the semantics of what the user is saying, rather than just take the keywords and go searching by that. Go ahead, Albert.
So why is it called an inverted index?
the linguistic search, the keyword search is inverted index because, see, usually a document has words. So one way of keeping it is that given this document, these are the keywords it contains. But if you invert it, what do you get? Given a keyword, what documents contain it? Think of it as the inverted map, right? Hash table. So that's what it is. And obviously the values are the list.
So basically, like then goes, looks at the documents and then kind of figures out the index.
That is right. So what you do is you take a document, sieve through it, extract the keywords, and then in the hash table, for each keyword, you put this document ID saying that this document is there. Right? You add it to the list of document IDs that are there. So that's what a search engine traditionally has been. But with AI, we have a different thing. And we saw how dramatically enabling a semantic search is. We did it with the classic case, text in, text out. You give textual prompts, and then you get back textual response. The AI searches through a whole corpus of text. But then we extended the idea further. We realized that the semantic search we were doing through, in this particular case, by using sentence transformers, which create sentence embeddings. It embeds it into a hidden vector space. And so you're doing vector searches. Now, vector searches is good. You realize that it's quite effective. What do you lose? Now, I want to give the big picture. See, think back to the BERT. The BERT transformer, if you remember, it took two segments or two sentences as input, right? And it passed it through the layers of the encoder, and then finally it produced the transformer heads and so on and so forth. And finally it produced, well, obviously the output, but one of the hidden representation outputs was the output for the CLS token, the initial token. And now from that you can do many things. So for example, you can see, if you treat it as a softmax input, which of the words in the vocabulary, right, or like, I mean, you could ask from that, a very simple thing you could do, not even the words in the vocabulary. You could ask this question: what is the probability, just simple logistic regression, what is the probability that these two sentences are close to each other, right? Because you use probability as a similarity measure or something like that. You could do that, and you can train a BERT transformer to be very, very good at it. Right? It's one of the classic things it could do, similarities between the two sentences. Now, why do we not do AI search using that? That would be the gold standard, isn't it? So imagine you're sitting with a corpus of 1 billion text, which is quite common. For example, in the previous company that I worked for, literally that was it. You had a corpus of 1 billion pieces of text, more than billions and billions. Right? If you give it a query text to pass a few billion inferences through a transformer for every query is not feasible. It will take arbitrarily long time. Whereas the expectation in search is that it should come back in the blink of an eye. And it wouldn't happen. So now, from that gold standard that AI can do, let us break it down and solve the problem piece by piece. So the first great milestone is the sentence BERT, and today we'll do the architecture for sentence BERT. We didn't discuss the architecture for sentence BERT. So far, we understood the classic transformer encoder decoder architecture. Attention is all you need. Then we discussed the second paper, the BERT paper. Now today we'll discuss the sentence BERT paper, but moving a little bit ahead to what it produces, what the sentence BERT produced for us was embedding of a sentence into a semantic vector space, a semantically relevant vector space. It understands two sentences will be close together if and only if they're very similar, right? And it somehow learns similarities based on the semantics of sentences. So when you do, and how it does that is the context for the afternoon, but given the fact that you can do it and you have projected it into a very high dimensional Cartesian space, then the problem becomes very simple. This query becomes a point, a vector, and around it, you have already all the documents pre-indexed into the vector space, projected into the vector space. Just go look for the neighbors, right? Now, one way of looking for the neighbors is the k nearest neighbor. Again, take this vector and compare its distance to all the billions of other vectors. That, while it is cheaper, for example, we use cosine, you can use cosine distance. Vector similarities are far cheaper than running sentences through transformer to look for similarity, isn't it? Significantly cheaper. But still you're comparing against a billion, let's say, documents, a billion vector points, that they're vector representations. So that is exact k nearest neighbor search. So then comes to our rescue. And before we get to how that problem is solved, remember that in very high dimensional spaces, you tend not to use Euclidean distance because of the curse that data scientists face, which is worse than any Harry Potter curse. And what curse is that? The curse of dimensionality, right? In higher dimensional spaces, everything becomes very far off from everything else, right? Or if you look at any one point relative to this point, all other points seem to be at the periphery of that whole space. It's just way, way out there. So you tend to use cosine distance or dot product distance. To recap, the advantages and disadvantages of cosine and dot product is cosine distance tends to favor similarities that are close by. They're short sentences. They tend to be more similar. But if you are comparing larger pieces of text, they tend to be favored by dot product distance. Are we together? They get favored by that. It's just an empirical thing you need to know. Then another approach, which is sort of a composite, is what you do is you take all the vectors and normalize it. When you normalize all the vectors, what are they? They become a point in a n-dimensional hypersphere. Just now, hyperspheres are hard to imagine. Just imagine a globe. They become points on the globe. And so you can talk about cosine distance, you can talk about dot product, they're identical. Or you can talk about the arc length or whatever it is, some distance. So that could be that, and you can be creative with distance measures, yeah? So long as you're aware what high dimensional spaces do to you. Now, what can we do having projected points into higher dimensional, into embedding, semantic embedding space? These are called sentence embeddings or vector embeddings, since many synonyms exist. So long as the meaning is clear from the context, let's just call them embeddings. What all things can we do from the embeddings? You know, if you remember, when we talk about data generally, when data, there's a generative force behind data. It is relative rarity to find data uniformly spread in a vector space. So when you look up into the sky, you don't find all the stars are randomly, uniformly distributed. What do you notice? You notice clusters of stars, which you call galaxies, isn't it? So clustering is natural. You look around, forests are clusters of trees, isn't it? Clusters of houses form a residential neighborhood. Clusters of these concrete and glass buildings form the commercial district. And they tend to form clusters, isn't it? And these clusters are just about everywhere, human body. Each of the organ is clusters of tissues of a particular kind, and so forth. So clustering is everywhere. One would imagine that if you project all these sentences into an n-dimensional vector space, you would expect clusters. So what would those clusters tell you about? They talk about points that are semantically relevant. They're similar. What do you say when many people are talking similar things? Generally, what do you say? You're saying they're talking about the same topic, isn't it? That's the definition of a topic. Topic is conversation or things about the same, about semantically similar things. Semantically similar conversations or sentences form a topic. And so by the very nature of projecting data into an embedding space, you have the notion of topic modeling. You see how naturally it follows from that. Okay? Now, topic modeling has many, many methods. If you remember at one time, and those methods are still there, they haven't gone. We use GenSim. GenSim used algorithm called latent Dirichlet allocation, LDA. Now, I won't go into those because this course is all about transformers. But just for you to know that any problem that transformers solve, there's a rich history in NLP of solving it by alternate methods. And so one thing that is often worth doing is whenever you solve a problem, a task using transformers, to go and check if we had solved this problem using one of the other methods, how well would it do? Now, generally, transformers these days tend to outperform, but not always. It is always worth cross-checking, right? Because there may be scope for improvement and so forth. So yes, the topic modeling comes out naturally from that. And not only, and you can visualize topic modeling, but you can say, how do I visualize a 768 dimensional vector space, or how do I visualize a 500, a very high dimensional space? All we can visualize is 2 and 3 dimensional spaces, right? So the trick is you use dimensionality reduction techniques. That is, again, something you have learned in the ML100 course, in the Introduction to Machine Learning course. There's a whole slew of techniques that takes the data represented in high dimensions and brings it down to a lower dimension. Sometimes the purpose is to find the most reasonable lower dimension in which most of the features or the substance of the data is preserved. But often it is also used for just human visualization to get a gut feeling of the data, right? And when you do that, when you use, there are many techniques. You can use principal component analysis. You could use another form of things called LDA, linear discriminant analysis. There are many, many such techniques you could use to project down data. Some of them are linear. And then there are nonlinear techniques, like, for example, TSNE and UMAP. A UMAP at this moment is generally considered by far the best. In most situations, not always, by far the more, for visualization purposes. Right? So when you UMAP that vector, you can get a very gut feeling of the topic modeling, right? You can see it in a page. And if you remember, the sentence bird documentation gives you an illustration of that. Okay? So do that on the classic data set that everyone uses for this, which is the 20 news groups. And you will see that it does a fairly good job of it. Now, you could use this for many tasks, right? So that's your sentence embedding aspect of it. Now, you could use sentence embedding for search, of course, k-nearest neighbor search, but we still have the problem, how do you search against a billion objects, because you're doing vector comparison. So we said that no, we have a cheaper way of doing it, because once again, in machine learning, there's a long and wonderful tradition of lots of creative methods to do approximate nearest neighbor search, ANS, right? And there are many, many methods. We in particular looked at FAST, SCAN, right? So these two. And there are more and more coming up and going, and HSNW, hierarchical navigable, small worlds map approaches, and so forth. But the gist of it is that these methods help you find nearest neighbors. But when you do that, you lose a little bit of accuracy. What will happen is, it's almost like you are, let's say that, how should I say? Suppose you're looking for some, to take an example, on the beach, you find some beautiful starfishes on the sand, or sand dollars on the sand, or something like that. And you are you want to pick the sand dollars. So if you just one by one pick up the sand dollars, you will take considerable amount of time. But if you're impatient, you can take a big bucket and just scoop the sand, right? With lots of sand dollars in it, hopefully. If you do that, let's say, and assume that the sand is rich with sand dollars, you don't just get the sand dollars, you get the sand also, but you don't want the sand. So you need a way to sieve out the sand. Does it make sense? So now what can you do? First is, suppose I tell you 10 sand dollars. Now, hand picking 10 sand dollars is easy. You get exactly 10. But when you scoop a bucket of sand out, you don't know whether it has 10 sand dollars or not. So you have a sort of a hyperparameter, how much to scoop out, how much results to bring back, because it will contain sand dollar as well as sand that you don't need. Or that's a metaphorical way of putting it. More realistically, it will contain, let's say that there are 10 real good answers there, but those answers may not show up, right? Because some of them are the not so relevant answers. You want to get the most relevant answers. So to have a good recall, to make sure that all the good answers are there and not missed, you want to scoop out a lot of sand. You want to retrieve a much larger result set. But it is cheaper, because the trade-off is, even though you're scooping a bigger result set, instead of just 10 result set, ANA is so far, so many orders of magnitude cheaper and faster as a search, that little bit of price that you pay, doubling or tripling the size of the results you get, or even 10 times the results that you get, is a very small price to pay. You get the whole bucket of sand, heavy bucket of sand. And in there are sitting your sand dollars, but you still have the problem of shifting through the sand and being left with only the sand dollars. Would you agree? So to do that, what you do is, now you can say, there are many things you could do. One easy thing is you could say, I will do the exact vector similarity measure, right? But when you do that and you're comparing against just 50 results, right, to pick 10 of them, or 30 results to pick 10 of them, would you do that? Putting 20 or 30 inferences through the gold standard, which was that put the query sentence and each of the sentences, each of the documents together through a transformer. BERT transformer is a cross encoder. Then produce a measure of how similar they are. That was a gold standard, right? We didn't use it because that was expensive, but we have sieved down the comparison to such a small subset now that it is now cheap to do that. So we can do that as a re-ranking mechanism. Does it make sense? As a final step. And when we do that, what will happen? Now our precision also goes up, because if we just preserve 10 and throw out the 40, there is a very, very high likelihood that you got both high precision and high recall, right? So this is the journey that you take to create something that you would actually deploy, because you got precision, you got recall, and you got performance and scalability, right? And remember, scalability matters, because through a GPU, like ultimately these transformers are, you can deploy it on CPUs or GPUs for inferences, right? Generally, you deploy it on the GPU, but when you deploy it on the GPUs these days are prohibitively expensive, and you're passing inferences through it. So what you have to do is you have to pipeline. And the faster the two things that matter, you want to make sure that the number of inferences that you pass through or you need per user query is small. If you do 1 billion inferences, like where we started out, per user query, you're doomed, right? And the user experience is terrible. But you have to bring it down to a very short number. 50 inferences, you can literally, or 30 inferences to pick 10 out of them. Easy. You can literally have a batch size of 30, right? Because they go as batches, mini batch. You can pass it as a batch of 632. So in one shot, you can do an inference. And that is what you want, isn't it? One query, one shot inference, ideally, right? And you get the result. So those are the considerations of scalability and performance. And finally, the deployment consideration is no user these days. Our attention span is such that in 4 seconds or more, we would have left the website, right? That's a fact, usability fact. So people already begin to dislike a place if it takes more than a second. So the gold standard is to come back in under 100 milliseconds, right? The rest of it is network latency. because it has to go through application layers and so forth. In fact, the gold standard is you want to, like in most enterprise, like for example, inference engines, if it is mission critical, you want to be under 10 milliseconds, 1 millisecond. You can keep on improving the thing, but for AI, 100 is supposed to be reasonable per query. So you want to come back in 100 milliseconds. So those are the practical realities. And so that was the intellectual journey that we went through. Now, on the theoretical side, we did two things, and this is, I'm still summarizing what we have studied so far. We studied two research papers. One was the great classic, Attention is All You Need. But when we did that, we took the paper, that paper, as we realized, introduced the transformer architecture, which is a sequence-to-sequence model. It has both the encoder and the decoder. And if you remember, I said language model is you take input, you create an abstract internal representation, a hidden representation, and then you decode it, that decodes it into whatever, into French, into Hindi, or just a summarized text, into poetry, into whatever, right? The output you can then think about, right? Decode it as such. And of course, now we are entering the world of multimodal learning that makes it even more interesting, but we'll get to that. Now, that paper, if you realize, it's biased. The explanations are very biased towards fast computation, because in those days, the biggest problem in the natural language processing world was that RNNs, LRUs, just LSTMs, etc. They were not really using the parallelism that was possible from these massive GPU farms, right? They were basically sequential, like compute models. As sequential compute models, it was its limitation. So the transformer's great breakthrough was not only that it brought the concept of attention, but from a computational perspective, now you could parse the entire sentence at one go, or paragraph, or whatever it is, at one go. In fact, you had to. There was no way you could give it one token at a time. So, which was a big win. And these days, research papers tend to be very benchmark heavy. Look, this has moved the state of the art by so many points, right? And so the flavor of the paper, the great paper, is very focused on the computational aspects and showing how this parallel computations does it. But in a way, that paper did not take and it's not supposed to take, of course, it's a research paper. It's talking to a community of people who completely understand what attention is and all of these things are. So it just went ahead and gave only the succinct breakthrough. But for us to understand, we went back to the foundations. We understood what attention is, what self-attention is, right? And what multi-head attention is. And we sort of took it down and took a slower approach to sort of building up to that paper. That was one thing. The second thing we did, the second week we did, is the BERT paper. A BERT tends to focus on the encoder part of the attention, the full classic transformer. And it is quite interesting that just by focusing on just the encoder part of it, it manages to do quite a few tasks, right? For example, for classification and for such things, encoder is enough. You just need a good hidden representation coming from the attentions. And from that, you have already gotten a contextual, a semantic understanding of what the thing is. And you can do your job. You don't need to necessarily put it through a decoder, right? So BERT and all its derivatives are encoder part. Now, and I mentioned in passing that the GPT and such they focus primarily on the decoder part of it, right? Because, and their main thing, for example, of GPT, the main crux is to produce the next token, isn't it? Remember, what does the decoder do? Takes the hidden representation and what it just produced to produce the next token based on that, based on the previous token, the next token in the hidden state, right? And so, which is exactly what, for example, ChatGPT is. Right? Well, ChatGPT is more than that. I don't want to say it is only the decoder of the transformer. There's a lot more going on in these large language models today. It isn't just that. You take transformers and you almost, a lot of the good things that come into it comes from reinforcement learning. It's a topic we'll end with, this course with. It is one of those optional days. It goes beyond NLP. But those of you who want to understand the full architecture of these newer large language models and why they work so effectively, you have to look at the fact that reinforcement learning and human prompting is a big part of it, of the training, right? And we will get to it. In fact, today I'll show you examples which will make you realize that compared to what we have, which does include reinforcement and all of this, the pure transformer of smaller size, not so large models, they can be impressive sometimes, but hopeless sometimes, right? And we'll see some of those situations. So we'll see the good and the limitations of it today. So that, go ahead. Yeah. I moved into new territory today. No questions? So either it's all crystal clear or you haven't understood much and you've forgotten whatever we talked about last week. Which of the two?
Hey, Asif, I have a question.
Go ahead, Mosmi.
Asif, most of it is tracking. One thing that you said about retrieving a much larger result set and sieving through it, right? How do you retrieve a much larger result set from like billions of
yeah. See, that was the technology of approximate nearest neighbor search. What you do is you have essentially taken billions of them, and in some way, in this vector space that you have, somehow you have, think of it as you have partitioned it into subregions, right? Either overlapping or non-overlapping partitions. There are many algorithms to partition, but somehow you have quantized it. Remember, we talked about all of those methods, quantization, etc., right? So let's take an example. Suppose, just to take a colorful example. Suppose you have a color, and there are 32 million colors, right? But you have one easy way that you can search through 32 million colors is, and you get a color and you want to find its nearest colors. You don't want to do comparison to 32 million colors. What you could do is you can create a vocabulary of just 256 colors. That's the 8-bit color depth. Now, just 256 colors. So you have 256 buckets, and every vector, every color that you get, you associate it or you index it by one of the 256 colors. That is the key. Value is, of course, this color. So then what happens? You have now reduced the problem set that first you find which bucket to search in, and then you are searching a smaller bucket. Isn't it, Masum? So now take this idea further. They're much smarter algorithms than the simple one that I mentioned. These algorithms manage to subdivide or partition the feature space into regions. So the only thing you do is, given a query vector, which of the subregions it goes to, which of the buckets it goes to, and you search only in that bucket, right? And you find the k nearest neighbors only in that bucket. Does that answer that, Masumi?
Got it. Yes. Thank you so much.
Not the same question, right?
Mm-hmm.
So when you pick up this whole piece of sand, do you pick up in different areas and get to a bucket, or do you get,
no.
You get the whole bucket together?
I got it. So Albert asked an interesting question. We use the metaphor of scooping a bucket of sand, one bucket of sand, and getting more than the $10, than the 10 sand dollars we hope for, but you'll get lots of sand too, or results that you want to ultimately remove. But where do you scoop the bucket out? So that is where the ANN algorithm is. The whole gist of the ANN algorithm is it tells you where to scoop from, right? In other words, that whole beach, it has subdivided into regions, partitioned it into little regions. And it says, this thing, go and scoop sand from here. And when you scoop sand from here, you'll get your sand dollars that you're looking for, relevant sand dollars you're looking for. Does that answer that?
Yes.
Yeah.
One question.
Go ahead, Abhijit.
I was just playing around with common words, like Hindi and English.
Mm-hmm.
So it's completely a different context. Like, when it was speaking, like, for example, I took Rajdhani.
Mm-hmm.
There's like restaurant also, there's a train also, and there's a capital also. So it completely messed up my like what I was trying to search.
the context. So it didn't know that like restaurant part completely. It didn't know, and it was just talking about trains. It didn't even talk about Delhi.
That
So
is
it's
right.
like it just started connecting Delhi, but it was more talking about trains. So here, what I'm trying to do is like if there's common words within languages and all that stuff, it can go in a different region where where there's no
Yeah.
correlation at all.
That is why, see, that's a very good question. So I'll repeat the question that Abhijit raised, a comment that he raised. He said a very interesting thing. In the Hindi language, there is a word Rajdhani. It possibly stands for, originally it stood for the word capital, like Washington, DC for the United States. Then it also stands for a very popular train. I mean, one of the fastest, well, India's version of high-speed trains, which means it goes at least 40 miles an hour on average, is Rajdhani, right? So that, but I think that now the Shatabdis are there, right, which go much faster, isn't it? And is Shatabdi the state of the art, or is the state of the art
They are much more faster.
much faster now?
Vande Bharat.
Vande Bharat. Okay. By the way, they were going to make sorry for the digression. They were going to make this high-speed trains using the Spanish technology. Has it happened or not?
Yeah, I think it's there somewhere from Mumbai to Delhi or something.
Okay, so those must be going like 200 miles an hour. Wow, nice, nice. Yeah, I'm fond of it because my father worked in the Indian Railways. He was an engineer there. So anyway, trains are Rajdhani, and Rajdhani is also the name of a very popular restaurant series, restaurant chain, right? So when you do conversion from English to Hindi, it gets totally screwed up. Actually, one of the weakness of vector search is that it is always looking for context to explain the word. When you give too few words or just one word and you search for it, actually vector search doesn't do so well. This is one of those situations where the trade-off is that a keyword search or a linguistic search is more likely to give you results, right? So, and again, that brings us to the side issue that sometimes what people do is they will take vector search, they will take so-called sparse or the keyword search, put it together, one bucket of sand from here, one bucket of sand from here, right? And then pass it to the cross encoder, right? And that too is done actually. So, but having said that, my suggestion is when you suspect that semantic search is available, and it's certainly true when you're searching in Google. When we started our Google search 20 years ago, 25 years ago, remember, the whole mentality was keyword search. But the world has evolved. In the transformer world, and to the extent that all searching, these big, mighty things are completely AI-driven now, you should assume that these things are at play. So you're much better off putting a narrative there rather than keywords. And we have to sort of shift our mentality. See, the world has changed, even though it looks the same. I keep telling people that the change is so foundational happening all around us, that the world has changed. We have just not caught up to it. So try that now. Give it the context, say the sentence, and then you see that the translations will be much more accurate, or your searches will be more accurate for these words.
I just like to play around, like trying to give it, confuse it more.
Yeah.
So let me see what you do answer.
Yeah. No, when you try to confuse it, you deliberately give it ambiguous context. Then you're trying to literally test the limits of how much semantic extraction a transformer can do. But then that is good to do, but then you realize that you're consciously doing it. If you give it a reasonable sentence, I really love the food at Rajdhani.
Yeah. Then,
Right, then, yeah. And I gave it 5 stars or something like that. But then, yeah. All right. So any more questions, guys? By the way, the technical word for words, term for words that have multiple meanings is homonym. Those are homonyms. Okay. All right. Any other questions before we start with today?
So the fastest train is Vande Bharat, 160 kilometers.
160 kilometers an hour. Okay.
That's the fastest one.
Nice. That's pretty fast, right?
Yeah.
That's pretty fast. Is it the Bombay Pune? No.
One day by that's I think Mumbai to Delhi.
Okay. So the Spanish thing hasn't come yet.
First class kind of. Even Rajasthan also have a first class kind of approach to the passenger treated like the Maya. That targeting.
That's a nice thing. Okay. All right, guys. So we have had a review. If you have no questions, let's take a very short 5-minute break and then we will continue with today. So guys, I've been giving homeworks and some of you have done. Now, those of you who did make some noticeable progress in your homework, please raise your hand in your Slack or in physically. Albert did. Praveen, you did, right? Oh, you did. You did. Very good. Yeah, Dhwani, you did, and Junaid has done. So actually, Junaid just showed me his work, and I would like us to do a small show and tell before we continue to the new topic, because we'll get again lost in the new topic. The show and tell is long overdue. So Junaid, would you like to take over?
Okay. Can you hear me?
Yeah.
Let me share my screen.
Shut the mic.
No, I'll sit some faster. I think. Mute.
So I guess you can all see my screen. Okay. So what I did was I down. Okay.
It's okay now. Everybody's.
Okay. Okay. So what I did is I downloaded all the data on PDFs from the National Institute of Health about diabetes. And I wrote some code to extract blocks of text from those PDFs and then feed that as the sentences to the model. And it was like taking 15 minutes on my laptop to run. So I had to serialize and deserialize it to once the embeddings were created to make it faster. So now I'll ask a few questions and see what answers it gives me. Okay. So oh, okay. Okay. The question is here. Okay. So first question was, what is diabetes? It gave me a very good answer. And this is like 10 to 12 big PDFs. The next question is, let's say, what is type 2 diabetes? And it gave me a very accurate answer, right? And let me ask one more question. What should be the diet of a diabetic person? Okay. So it gives me the diabetes food pyramid. It divides the food into groups. Right, that is a good answer. Any more questions that we can try?
Maybe you can ask, like, what's the diet of a diabetic person? Or can argue that. Just kidding.
Yes. So I think that's it.
Affect all ages. Does diabetes affect all ages?
Okay, let me ask. Yeah. Yeah, can affect people at any age, even children. Yeah. So
This is basically just a search. Right? You're giving
yeah, this is
search. It's
Ye-
not like
Yeah,
a tag.
semantic search.
it's semantic search.
Correct.
Yeah.
Here, there's a question on,
Okay, there is a question. What's the
Stacks.
question? Can you-
you know,
What
what
are the complications
are
of
the
diabetes?
complications of diabetes?
The most serious problems caused by diabetes is heart disease. So it's kind of answering all the questions.
I think somebody's asking, can we see the corpus? Corpus is the PDF file.
Yeah, the corpus is all the PDFs files. They are available on the web, on the National Institute of Health Diabetes website. But you have to do some work to extract the text from those PDFs. If you just extract line by line, it won't work as well. You kind of have to extract blocks of text, and each block becomes your sentence.
Did you use sticker?
I used a library called in Python. It's called MUPDF.
Oh, no.
Yeah, so there are two, PDF Plumber and TYMUPDF.
Okay.
So those are in my requirements.
So I would typically do it in Java, like some of these tasks, right, to make it faster
Uh-huh.
on servers. Typically do text extraction from PDF in Java.
Okay. Mhm.
So how large is corpus?
See, when I created the embeddings and then serialized them, that file is like 18 MB. Yeah, 18 megabytes.
Nice.
Yeah.
Okay. Thank you, Junaid.
You're
And
welcome.
Vani, you're ready with your demo?
I can show mine. Hello, can you hear me, Asif?
Asif is on mute.
We can all hear you.
Oh, you can hear me. Okay,
good.
thanks, Kate.
So,
I don't know if he can hear me.
so we can hear you. In the time you're pulling up your work, I have a question for Junaid, the one who demoed just now. So can we have a look at the corpus that you created? Like, I just want to know if the query sentences were very close to the, the responses, the blocks of text that you copied. Hello?
Yeah, we can hear you.
Sure.
So
Is that
this was just from like the last assignment where Asif said that we should do scan instead of using phase. So I have two different codes, I think. So this is one method, which was using dot product. And so this does the same, has the same features as the phase one, except it's a lot more simpler, I would say. The second, so should I like run the code? So it's like a simple where obviously it's not within like a user interface model. So you have to actually type in the query beforehand. But it was the same thing as before, where if you type in golden retriever, it will give out something close to the files relevant to it. That's
It's running at the same time.
yeah. Oh,
So you have to run it from the.
yeah, I have to run it. I just have to run the corpus. But meanwhile, yeah, the second one is this one has its own class and everything. So this one's a lot more easier to use with the user, where so it asks you like, or it asks you to type in a query. In this case, since Jupyter Notebook doesn't have that like user interface where you can type in the user input, this one is simple where you change the query and it'll present this data here. It's a lot more cleaner, I think. but this one uses cosine scores rather than dot product. So that's probably the only difference.
There is a widget. The way to get mirrored,
Mhm.
Jupyter allows that.
It does?
You have to use the widgets.
Okay, okay. Because I know like at least for the other stuff I've tried, it works on Python very easily. That's why I
Because
think-
it gives it to you on the command.
Yeah.
But in this, it will be a widget. It will produce a UI widget. It
Oh,
will
okay.
give it to you.
Okay. But
Very
yeah.
nice, very good. And this is good. So you got pairs to work. Very nice.
Yeah.
Anyone else would like to?
I can share. Can you hear me, Asif? Okay, I'm going to share my screen. Can anyone else hear me on Zoom?
Yes. Yes.
Okay, I'm going to share. I don't know if he is going to ask someone else to share, but 1 second.
We're just seeing the Slack channel.
Yeah, I think it's Asif's screen actually. Okay, I don't want to unshare his screen. I'll wait a second.
Okay. Asif Kashish is waiting to share results.
I think we cannot hear Asif because Asif's mic is mute.
Yeah, it looks muted. I
Well-
can message the Slack channel actually, the one he's on. Okay.
I'll repeat what I said. I don't know if anything got recorded, so I'll repeat what I said for a moment. See, with a rich variety of transformers and transformer architectures coming, and many problems being solved by using the transformer architecture in creative ways, one of the realizations we are coming to is that there is something quite fundamentally right about the transformers, powerful about the transformers. We were thinking of a neural network in terms of the neurons and the edge connections, because it is the weights on the edges that we update. The training process is finding the best possible weights of the parameters. And we do that through backpropagation and gradient descent, some form of adaptive gradient descent. But now there is an increasing feeling that while that is true at the atomic level, it's just like, a protein molecule is one analogy from biology could be. A protein molecule is a fundamental thing, or amino acid is not just all the atoms. It is a particular configuration of the atoms, and it makes amino acid provide a functionality. And so all proteins are made up of amino acids in some sense. So there is a close analogy between that and what's happening in neural networks. We are realizing that somehow these attention heads and these transformers are sort of like, they're sort of like the amino acids that put together can create all sorts of proteins. Right? And in the same way, by re-architecting the attention heads and how many you put and where you put many encoders or the decoders and things like that, and putting things before it and putting things after it or chaining them together, we are creating various transformer architectures, and it's become a zoo. Just like there's a large catalog of proteins, we are creating a virtual zoo of transformers architectures. Now, not only are we creating a zoo of transformer architectures, there's another thing that's happening, which is interesting. So let's take the one that we talked about last time. The paper BERT showed that if you train BERT on that corpus that it was trained on, it could do at least 6 tasks in which natural language processing tasks, classification, question answering, continuation, finding the masked word, and so forth. And it could do, and at the time BERT was published, it achieved in 2018 or 2019, it achieved state-of-the-art results, isn't it? But the question comes, when you train something on a generic corpus, it can answer general questions. But if you look, the world is divided into tribes in some sense. There is the financial people, there are the techie people, right? They are the medical crowd, and they all have their own sort of a dialect within the larger English language. They use terms in a particular way. So instead of putting a general purpose corpus of text to train this neural architecture, what if we trained a transformer, exactly the same architecture, but we trained it on specific corpora? For example, for the financial world, let's take a corpora that is only made up of things spoken in the financial world. It is not hard to gather such a corpora. And what if we do that? Now, you can do that in 2 ways. You could just take a massive amount of financial documents and then train that from scratch. Or alternatively, you may be better off first training it to the general corpus, and then saying, okay, now further let me train it with the financial corpus. Are we together? Fine tune it. And then you get a fine-tuned BERT model for the financial world.
Yeah, they did this previous Bloomberg GPT.
Bloomberg GPT has come up, exactly, yeah. Yeah, and then if you look at the Fin something on Hugging Faces, there's another collection of the older ones, right? Today we'll use one of the older ones, right? But maybe actually as an exercise, why don't we make it a lab? Let's use the Bloom one, right? So what you see is that there are 2 degrees of freedom. You can create completely new transformer architectures, or you could take an existing architecture and further train it on specific corpora. Right? Domain-specific corpora. You can adapt it to a domain. And both ways, you get some really good results. Now, transformers have proved so effective. Like I told you, that natural language processing, which used to be RNNs, LSTMs, GRUs, nowadays are mostly transformers all the way, with occasional use of LSTMs here and there and so forth. The world has changed quite radically. All these transformers are fortunately donated to the open source community with one conspicuous absence. Which big transformer is absent from the open source community? Well, GPT-4 and ChatGPT and GPT 3.5. The GPT is the latest OpenAI GPTs. Right? They're not releasing it anymore. Right? So, but by and large, the community, all these companies, they spend gazillions training these transformers. And isn't it an amazing thing that the spirit of collective research is there, and so they all release it to the open source community. Now, the biggest aggregator in the open source world of these transformers, like the watering hole, if you want to go get transformers, where do you go to? You go to Hugging Face. So Hugging Face website, and I'll share that now. Or am I sharing that? What are you seeing on my screen there?
The Slack channel.
Slack, that's the wrong one. So this is the website, huggingface.com. And if you come here, let me increase the size. You go to models. And I want to just walk you through the models. You notice, first let's focus on the left and see what sort of models are there. Multimodal learning has become dominant. The boundaries between various subfields within AI, like computer vision used to be its own world. And when people use computer vision, the quintessential example that came to everyone's mind is self-driving cars, right? Or finding what is things like that. classifying an image or things like that. Then there's the world of natural language processing, text and sound. But then we realize that NLP is beyond text. It also has to do with sound, isn't it? So, but today, those boundaries are blurring. So if you notice, I started the course with multimodal learning, because multimodal learning is the new frontier where the boundaries between all of these are being blurred. You can ask a question in text and get a response as a video. Or you can give a textual description and literally, I mean, there are some of these lovely, lovely examples people have created on the web. They have used Midjourney and a combination of a ChatGPT and Midjourney to literally take a textual description and produce, and of course, DALL-E 2 and stable diffusion and everything, and ultimately produce a whole video from the text. So imagine what transformative effect it is having on so many industries. I hope we saw that you could ask questions visually and get answers, and we'll do some of that today. So that is multimodal learning. Then there are computer vision tasks that it can do, but we are going to focus on the NLP task. Some of the basic NLP tasks that you can do is, the oldest is classification. Right? Classification comes in many forms. For example, the easiest one that people look at, and still an imperfect one, but the easiest one that comes to mind is sentiment analysis. Very useful in commercial world is the opinion expressed, is the comment, is the sentence of positive sentiment, neutral sentiment, or negative sentiment. Right. So that is an example of classification. You're classifying in 3 buckets, 3 labels. Another example is, for example, classifying based on what the subject is. Is it talking about science, politics, right? Or history? What is it talking about? That's again an example of text classification. So take text and classify it into a target space, finite target space. Now, a token classification to determine, for example, one easy one is, when you have a text and you break it up into words, into tokens, the parts of speech, is it a noun? Is it a verb? Right? Is it an adjective? Is it a proper noun? What is it? Comes into that. Question answering, we can answer questions, right? Then translation, can you translate the text from English to, let's say, French or Hindi, or to whichever language you want, Mandarin, right? Vietnamese, whatever, right? Or you could do another form of translation. You could say, not translation, but sort of similar to that is a neural style translate. Translate this bit of text into a sonnet, right? Make it rhyme. So there you're applying a different style to the text. Could we do that? Or write it in Shakespearean language. Amazing thing is we can do all of that today. And in the course of this workshop, through the various projects we do, we'll do all of it. And in a way, from today, I would like to start the bigger journey of exploring all the things that we can do with transformers in the lab parts of it. Then comes summarization. Quite often you see a long article, and then you say, where is the TLDR? Right? Where is the summary of it? And can it produce summarizations? Now, summarization can be in 2 forms. It could be just extracting the seminal sentences from the text, or it could genuinely be rephrasing it but summarizing it. Right? So there are aspects of it. Conversational. Now, have a conversation with the transformer, as a chatbot. Could you do that? Now, adjacent to conversational is text generation. Can we have the system write new text that answers your question? Right? Very close to question answering. Like Junaid just showed you a demonstration that on the diabetes data set that you could ask a question and it would produce an answer. Right? But could it generate new text along with that? Now, there the mileage varies actually. Yeah? So don't be too impressed with it. Text-to-text generation, again, what we just talked about. Can you do one form of text to another? fill in the blanks, the original way that BERT was tasked, mass language model. There are gaps in the text, fill in the gaps. Right. And by the way, that is not just true of gaps. Today, you can render a person's face, for example, from a partial face. Right. And quite often, it is very, very close to the real face. So it's a fill in the blank exercise, isn't it? A certain part of the face is occluded, is masked, or simply not visible because the picture is taken from a certain angle. And you're asking, can we now fill it in and make the full face? Right? We can, actually. You can literally unmask a person. Right? So, well, I suppose beware next time you feel like going into a bank with a mask. So, sentence similarity is something we have been doing using sentence BERT, you know that. But one of the interesting things is this cryptic thing called a zero-shot classification. Right? And I'll speak to that for a moment. What is zero-shot? And we will now go into the lab. Zero shot is this. See, the biggest problem in training, let's say that you're training a transformer or AI system for text classification, right? So what do you have to do? There is this very, very labor intensive part that you outsource to third world countries. Take the text and go label it. People are doing, not even that, I mean, a lot of work. When you work as a data scientist, you'll be surprised that the first thing they'll give you, think of it as a rite of passage. You join an organization, you're thinking that you'll do some great algorithmic, neural architecture. You'll sit and craft, and you go and sit in your office, and the very first thing they give you is, okay, why don't you sit and annotate all this text and label all this text, right? Somebody has to do it, and it's the equivalent of you joining a team and they ask you to sharpen the pencils, right? You sit and label the data and annotate it and so forth. We all have to do it. And actually, there's a lot of learning. The first thing that you learn is that quality of the input data drives the quality of the precision or the goodness of the model at the end of the day. It's a worthwhile lesson to learn. Now, one of the things people have been asking is, wait a minute, suppose I trained a transformer to classify into something, text into some categories, whatever the categories may be, certain classes. And it doesn't matter what the classes are, right? It has picked up this, it cannot possibly classify unless it has picked up the semantics of the words. It has a semantic understanding of the text. If it does have a semantic understanding of the text, can I do this? I give it new labels. Let's say I give it labels now and say education, science, politics, 3 labels or something like that. And I basically say, is this text about education? Is it about science more? Or is it about politics? But it has never been trained on any label data containing those 3 as the labels, with sentences with those as labels. Can it do that? It's sort of like a holy grail. It seems like, how in the world would you do that? If you think about basic classifier training, you have to train with data, right? But you're saying that, no, we are not going to train it. Take a pre-trained model, which was doing something completely different. But can it solve this problem? And the magical thing is, quite often, and more often than you think, it can solve the problem. Or at least it can solve the problem enough that instead of annotating it with labels, you can just review and correct the few mistakes. Isn't that a good thing? It accelerates the process of data generation, data preparation. And that is when you can do it without ever showing the model or training the model on this task, data specific to this task, that is called zero-shot learning, right, in NLP. Now, zero-shot learning has a bit of controversy attached to it, because people always used to say that even if you can do it, it can't be that good as actually doing the hard work of preparing labeled data and then passing through it. Right? Things have improved. Today, when it came out, zero-shot learning's accuracy was sort of needed improvement. But today, as more and bigger models have come up, zero-shot learning seems to be doing quite well, acceptably well. And certainly as a preliminary step that reduces the quantity of work you have to do in creating labeled data by a huge amount. Now, sort of the middle ground between zero-shot learning and the traditional training of a classifier with lots of labeled data is to take a small collection of labeled data, few shots, right? Just a few bits, and then do that. So how does zero-shot work? Can you imagine? How does it work? In the case of target variables, how does it work? Hint, think of what we have done in the last two labs. Sentence transformers, what do they do? What do sentence transformers do?
Do semantic search and find the nearest neighbors.
Embeddings. So for example, what could you do? Instead of treating the target space as labels, you could convert the labels into vectors, embedding vectors, isn't it? And now what you have to do is you let it classify. You just know that whatever it was trained on, where does it go? Right? Where does what it was trained with? The old, let's say the old labels for ABC. There are many ways of doing it, but one way, A, B, C, D, E, F, G. Now you just map your A, B, C, D, E, F, Gs to this, your vectors, your new vectors, like create their embeddings, create the embeddings of these vectors, these new labels, and basically match old labels to the new labels in a way. Am I making sense? You map it to the new labels. Now you're in a good shape. All you have to do is predict which of those, where does it go?
So it's basically overlapping to see.
Yes, exactly, to see what. So
like two keys that you have one set of keys.
Exactly.
Pointing.
Yeah. So you realize that at the end of the day, right, the resolution of mysteries are very simple things. Once you get the concept of embedding, you'll realize that vector spaces are magical things, right? Especially with dot products.
But how would you do it? So let's say if you had a pre-trained model, and then now you're going to train it on the
No, you don't train it at all. You're taking that model and you're saying zero shot means no training, but I'm changing the target space. And what I'm going to do is I'm going to say, this is the label you have to produce. So now think internally what will happen. Internally, the transformer will first predict into the original space. From the original space labels, it will map to these labels through an embedding, because those labels and these labels are all projected into the embedding space, and everything that we have done in the last two sessions comes into picture and you can map it. It's one way of doing it. Right?
One language to another language.
Vector embeddings, yeah. Proximity, right? You're just looking at the nearness. This label, politics, is close to which of the labels here, right? That's all. Yeah, that is it. Vector closeness, vector similarity. And so you can do zero-shot learning. Let us do these tasks.
Oh, I see.
Yeah.
Ask one question.
Not today. Don't even mention it. It's for the next class. Right? We will do it next Saturday. One shot, few shot. No, we will do, but hold that thought.
Ask one
Let's
question.
keep
So
some
sorry,
mysteries
I'm not
for
seeing the
some
screen.
time.
That what screen
So-
are you sharing? Is it the board or something?
Now, after
So
all
I
the
just see the
conversation, let's go
Just
and do
Hugging
something.
Face library.
So,
Okay.
I will give you guys these files, but just listen to me and then immediately I'll release these files. I just realized. So you have the semantic search already, right? Let's take baby steps with Hugging Faces. Hugging Face. Hugging Face has made, so what's the contribution that Hugging Face brings, library brings? It is first the aggregator of transformers, pre-trained transformers, right? So when people talk about pre-training, remember that today we think of training as made up of two parts. You don't usually train a transformer from scratch because that would be horrendously expensive and you would need ginormous amounts of data. So what you do is you start with a transformer or a model that has been trained to something adjacent to your problem. right? And you try to find the closest adjacency. Take that. So that model which has been trained is called pre-trained. And on Hugging Face, all those pre-trained models are published. Now your question is, how do you take one model? You can either just use it, because if you have an exact map to your task, just use it. And now the surprising thing is, you'll be in enterprise, especially in things like customer relationship management, sales, marketing, and customer service, and all of these domains. And enterprise, error logs and things like that. It is surprising how often, already on Hugging Face, you'll find something that pretty much works even without needing any further work. You just get a pre-trained model for what you think is adjacent, but it sort of works so well that you don't even bother further training it. The further training and refining it for your thing, your problem domain, with data, labeled data for your things, is called fine-tuning. Are we together? So 2 steps, pre-training and fine-tuning. And when you pre-train the model, now let's bring in some language that you find very common in the Hugging Face libraries. They will use a pre-train, right? When you say pre-train and you give the name of give the name, it is the namespace or the name by which that model is registered with Hugging Face. Are we together?
Can you repeat, please, once more?
So when you publish a model to the Hugging Face hub, it's called the hub, you will have to give it a unique name. Give it whatever you want to call it. You want to call it the abracadabra, you can call it the abracadabra. And thereafter, anybody who wants to use it will refer to it by abracadabra. Right? So let's search whether abracadabra exists or not. We'll find out. So that's a convention. But those models, the presumption is they're pre-trained, and they often use the word checkpoint. Like some things that explicitly hope that you need to do further work. They just say that we have checkpointed at this much data. You can make further progress with it. Yeah. So you'll come across all of these notions of checkpointing and pre-training and so forth. But that should now be familiar to all of you. So let me take the simplest example, because think of it as sentiment analysis is the hello world of natural language processing. Right? By the way, sentiment analysis even today doesn't quite get sarcasm, though it almost gets it now. The transformer models are getting smarter and smarter. A few years ago, the joke was, or the sarcasm was on sentiment analysis, that it fails on sarcasm, right? But now, well, all things grow, right? And this baby is grown up, all grown up now. So we'll see. Actually, in this example, I didn't do sarcasm. So let's take it as a homework. In the lunch, try to create very sarcastic statements and see how well some of these things do. So how does Hugging Face? I'm using this as an example of Hugging Face. So the value Hugging Face brings beyond just aggregating is an API that is so dead simple that for most tasks, you can get done in like 4 or 5 lines of code. Imagine, right? Vast amount of intellectual, deep thinking, right? Deep thoughts and research, mountains of research, and gazillions of dollars in training these massive transformers. And you can use it just like that with 3 or 4 lines of code. Isn't that amazing? Right? That gives you the value of open communities. So this is it. So now we take the sentiment analysis. What you do is this line, first line from transformers, import pipeline. So transformers is the library module in Hugging Face. Guess what it is about? It's this vast bundle of transformers, right? All of the transformers have been standardized into one particular way of usage. Use the transformer library of Hugging Face, and then it sort of has standardized on all the transformers properly. Or rather, other standard, if you create a transformer, because Hugging Face is the standard, there's a huge pressure to conform to the norms here, right, to do that. And also it provides you a transparent layer over whether it's written in PyTorch or whether it's written in TensorFlow.
It's almost like an app exchange for transformers kind of thing.
Absolutely. What App Exchange is for Salesforce, or the App Store is for iPhone and whatever, except that it's free. There's no charge, right? So now a pipeline is quite literally what happens is when you do a pipeline is a function. In the simplest form, it's a function that takes the name of a task. Are we together? So more specifically, the first argument, as you know, in Python functions, you don't need to give what is the variable. But if you were to be more exact, you would have said task is equal to sentiment analysis, right? But you don't do that. Convention in Python is the first argument is not named, but it is a good idea to name arguments if you want to, because you're being very explicit. So let us do that. I added to it. Now this transformer, we got, what does it return to us? It returned to us a classifier. But there is a problem. How did a classifier come across a transformer? Isn't a transformer meant for many use cases? For finding the hidden words, hidden masked words, for classifying, for completions, for whatnot. So a transformer is a building block, right? It's a building block. It is not a classifier, but what you need to do is you need to screw in a classifier at the tail end of it for it to be able to predict. How do we classify? Typically in machine learning, it's your logistic function, softmax function or something. You need to screw in a softmax head or a logistic head at the end of it, isn't it?
So you're mapping it in that full thing of SAM. You're trying to give it an area where it has to search from, and that is the classification layer.
Oh, no, forget that SAN thing, the search thing. We are not within that idiom anymore. So forget that metaphor for now. We are saying that when you do a complex task, there are many, many steps involved, right? Quite often, so it is not the work, it's just not that you throw the way the transformers are created, they're meant for many tasks. So they are basically incomplete objects. They're called headless objects, right? Because the purpose for which it will be used is not defined. So you have to screw in. So whenever you write a code, whether it's a neural network or whatever, remember, what do? At the end of it, the last layer of a classifier is usually what? A softmax or a logistic unit. Reviewing from your introduction to machine learning course, it's all usually that, right? So what do you need to do? Transformer, screw in a classifier at the top of it, the thing. So that is good now, but here's the problem. This transformer is expecting input as tokens. Who builds the token? What you are sending is text. So you need a tokenizer, right? So there are things you need to do before and after. The transformer is the one, but actually what happens is the tokenizer also you do with a transformer, right? There is another transformer which is specifically trained to tokenize and detect parts of speech and do all sorts of fancy things and convert the word into a word vector, embedding. There's tokenizing, embedding, and then that embedding goes into your transformer through all the attention and all of that, and out comes some logistic, some energy is what I call voltages in some sense. And those voltages must be softmax to produce your probabilities, which you need for the classifier. Right? That's one way of thinking about it. So it is like a garland that you have made from which has many beads in it. Right? It's a pipeline, or more prosically, it's a pipeline of many components. And so what Hugging Faces has done, it has given you two choices. You want a bicycle, I can just bring out a bicycle and give it to you. Or you can say, I need a handlebar, I need chains, I need seat, I need frame, and then you sit and put it together. You get both the low-level approach and the high-level approach, right? So if your task is served by the high-level approach, just use it. And it is surprising, the last I checked today morning, there were at least 16 or 20 tasks that come And in fact, 90% of your common tasks that you would use, they come already baked in. So somebody has already created the pipeline for you. Hugging Face Library has already created that pipeline of all the necessary components for you. The only thing you need to specify is the meat of the matter, which transformer model you are using. Are we together? And even then, if you don't give it a name, there'll be a default one that it will pick and just say, ah, this guy didn't give a name, let me use this. Are we together? But everything is pluggable. You can change the tokenizer. You can change the model. And you can change many, many things along the pipeline. That's the nature of this. So let's start with the very basics, the hello world. We created a sentiment classifier. So using the pipeline function, but the pipeline, as you know, underneath is that. Now, if you look at this pipeline function, in some sense, it almost behaves like a constructor of a task. Like, you know, in object-oriented programming, you would think, except that given a task argument, it manages to construct a model in the traditional machine learning sense. It does a job. Now it is ready to serve inferences or do whatever you want it to do. So now moving forward, and when you run it on your machine, guys, it will take a while because these models are, oh, but what's the size of some of these models? Big. Now, a good sentence transformer is the Distilbert. So let me explain. It says Distilbert, base, uncased, fine-tuned, sentiment to English. Like as cryptic words go, this takes a cake. So let's break it down now. BERT is big. And when you run BERT, especially the BERT base or BERT large, the two BERTs mentioned in the original paper, you start soon being troubled by the slowness of inferences. Or when you have a lot of inferences to make, throughput is low, or the compute cost in GCP. So one of the things people did is they said, okay, can we take a BERT, a much smaller model that is almost as good as BERT base, right? So that architecture is the Distilbert. And it's a boon for those of you who insist on doing machine learning on laptops, which in my mind is the definition of insanity.
Well, is it done? No, it's not done.
At least connect to a workstation, powerful workstation in your house. Use the laptop to connect to it or something. Like, for example, where am I doing this? Oh, I'm using a laptop. Or am I? Now, this laptop is actually connecting to, look at this. Where is it connecting to? It's connecting to the Linux server there, right? So don't do that. But anyway, if you're doing it on small machines, Distilbert is pretty good. Base, Distilbert itself has various sizes of the model. Base will usually be the default one. Now, sometimes they also use the word small, medium, large, right? So base, uncased, not case sensitive, training on the data. Fine-tuned. Fine-tuned means not only has this model taken the normal training through all the corpus for all the wide variety of tasks, it has been further fine-tuned with something called SST to English. What could it be? Sentiments. Yeah. And I suppose so. I don't know exactly what SST to English is. If I were to guess, it is that they have only looked at English sentences, sentiment sentences, right? Possibly that could be it. But enlighten me if you find the real meaning of it, the rest of the phrase. But that convention you'll see followed. Right? So now you'll see that for different models, you will see these extensions used.
What is fine-tuning?
Fine-tuning is the second part. So you take a transformer which is made for many tasks, and then you fine-tune it for your particular task. And by giving it your data, you give it further data for your task, labeled data for your task, and you continue the training, right? Further training.
So like you train and then you validate the models. So you still need to do the same.
No, now what is happening is we are saying training is broken up into two parts. Pre-trained, and you get pre-trained, and then you have to. So it's somewhat like a door. You go to Home Depot or Lowe's these days and you buy a door, and the door has no color, and you need to paint it. So think of it like that, right? It's more than that. Actually, you're actually giving it labeled data. You're further training it specifically to your task. And in fine tuning, the performance does fly up. So you have to do. If you have data to fine tune it, do it. Good thing is it's not expensive. You can do it on reasonable hardware. Right. So we did that. Now we can be more explicit. This is a best practice with Hugging Faces, guys. It is always good to know which model you're using so you're not surprised. And when a better model comes up, you can plug in the name, right? So how would you know if a better model has come in? And this is part of the culture of Hugging Face. Hey, let's go and see how it is. Let me take something. What am I taking? Sentiment analysis here, somewhere here. Do I see sentiment analysis? Feature. Okay, we don't have to do that. We can go to sentiment analysis. Sentiment. Right. And oh no, it just came up with results. If we just search for models, filter by name or filter by task name. So let's go to sentiment. Well, okay, that's a classifier task. So it isn't specifically given. Let's filter by sentiment. Look at this. We came up with 2,000 models that can do sentiments for us, right? So why do you think there are 2,000 models? Surely they haven't invented 2,000 architectures, because creating a new neural transformer architecture is painstaking. What they have done is they have fine-tuned on specific data sets, right? So for example, a Twitter Roberta base sentiment, what does it, I'll tell you how to interpret it. They have taken a corpus of Twitter tweets and presumably labeled it. Then they have used the Roberta base model. Roberta is another bird variant, Roberta. And it's also defining quality is that it's relatively faster, smaller, and big model. So you use that base, and it has been fine-tuned for, like the fine-tuning is done with the task of sentiment analysis. Right? That's how to interpret it.
So they took the Twitter data to then fine-tune?
Yeah. Somebody sat and labeled it and then passed through it. Yeah. It took a Roberta base and then fine-tuned Roberta base to this. And so the model that you get it, and people often use the word checkpointed or something, that model, they uploaded it here. But now suppose you want to go one step further. You want to only take Twitter tweets that talk about COVID, let us say. What would you do then? Twitter about COVID. Now you need to go get only COVID specific data, go label it, and then further fine tune it, isn't it? Go through further training of this model, and you can go on and on and on. You get the idea, right? Yeah.
So it is also categorized with the best one on the top, right?
Yeah. So the sorting is most downloaded, not necessarily the best. So sometimes the best, that one just came out. For example, he talked about the Bloom for the financial. And we will use that actually, the Bloom sentiment. And let me use Bloom. Yeah. See, this is it. A Bloom fine-tuning sentiment model with so many things, right? And if you look at this, it will talk about big signs on the, oh no, this is on the IBM data set. There's a fintech. It's a Bloom and fintech. Fin. Yeah. Finance. You can't.
So Asif, I have a question.
Okay, we'll come to it in a moment. We'll come to it. Huh? So.
Hello.
And why don't we go to a lab and you'll see this example. So you take one distill bird, you give it a sentence. The NLP sessions have proved useful so far. I know that you all are violently disagreeing with it, but
hello.
Let's see. What does it say? It says that if somebody says this, the sentiment is, it's pretty confident it's a positive sentiment. Right? Well, you may say,
hello.
let's try a look. Oh, so I have to start from the beginning. Sorry.
Look, can anyone hear me?
We can hear you.
Yeah.
Yeah, I think Asif is not picking up the audio from this Zoom.
Let it come through. So one thing
I
to
have
be
a
sure
question
of,
about
guys,
the
if you're going to
pre-training.
do transformers, oh, 1 second. So guys, two things you have to remember with transformers: good internet and good GPU, right? So which means that it's a good idea probably to buy NVIDIA stocks, or maybe it's already gone up too much. AMD is now coming up with a competition. I mean, the thing which is pretty good. So guys, let's look at this sentiment. It said, it still says positive. Nah.
I think it's also sarcasm is in the way you say it.
Make it sarcastic.
Really?
Yeah, really sure.
Not. Let's try this. Right. So by the way, the same thing when I did a couple of years ago, a similar thing, it used to fail miserably. It wouldn't get it right. But now you can see that these models are evolving, isn't it?
Can we say, like, are you sure the NLP sessions have
Yeah. Why don't we do another one? Tell me the text. And then, guys, I apologize to those of you who are putting it on the chat. I'll come to you in a moment. What is the sentence you want to give?
I was thinking, are you sure the NLP sessions have proved useful?
Let's try this. Right, and then sentiment. Is sure. You're questioning its validity. I hope it's not shared quite widely. All right, now let's take a few more. See, if you look at it, actually some of these, it's become so difficult to reach customer service for my product, right? You're not using the word sucks or terrible or things like that. No. It's endless call waiting to begin with. It gets that. But then I put a phrase, oh, fraptious day, kalukale. Right. Now, do you notice that there is not a single word that makes sense except for oh, right? Or day. Oh, day are the two. Fraptious, kalukale are both cooked up words. And yet it is able to give you a score of 99% positive. Why do you think it has done that?
Because of the exclamation.
Sucks! Exclamation.
Is that a pretty big or something? So capital C.
No.
Because it's filling it in. Like it ignores the words that don't make sense. And then fills
Oh, day. Oh, day, no. No. So let's try it. Let's try it with an example. Give me something that you think is, again, if you just did all day and see what happens. I will comment this one out. It's positive, right? But its score is different, very high confidence level. Suppose I say, see, just exclamation mark. It still says positive, just an exclamation mark you can see there's a bit of a limitation here. Is not, should be not positive. So what can we do with this model? No, this is a very basic model. Distilbert is a very basic model. Replace it with, and one of the lessons we are learning with transformers are bigger is better, right? Use one of the larger language models. Right? And so I leave this as an exercise for lunch. One of you find which of these models you like in this. It's a download, but fortunately we have a gigabit fiber here. Try it. Wi-Fi might not help you, so you might want to physically connect your laptop to this. But by the way, 500 MB is not a big deal. You can download over the Wi-Fi also. So, but I try to create, see, I'm trying to create examples that will hurt. Let's take a fintech example. You create a text, a fintech one. This is the one, the process, Finbert. Finbert is a clue that it's a bird for finance, right? Typically, people, when you see a slash, it means that Process AI is some company or organization. And we use it to do a text on this. The trading is very bearish today. Then today the market rallied and NASDAQ gained, but not much. I'm deliberately creating things that are a little bit ambiguous. It will come out and say the first one is neutral and the second is a bit positive. Right? It is positive, right? Then why the trading is very bearish today? Why is it a neutral statement? Because the bears win.
That's what?
The bears win. Right? Remember, one man's good news is another man's bad news in the financial market. Right? Whenever there's a buying and selling of stock, one believes it's a good time to buy, another is sure it's a good time to sell.
So what if you say bull?
Let's try that.
Then it should be positive.
We'll find out. Oh, I have to first run this.
It's like very simple, just a few lines of code.
That is it. That is why it's literally the hello world of NLP. So anyway, while this comes through, let me show you the result because it has run on the other server. If you give it to the normal sentence classifier that we just created, which is not fine-tuned on financial data, it certainly gets it wrong. When it says it's very bearish today, it gives it a positive score. It is not a positive news. It's just, winners and losers statement. The other one is statement, today the market rallied and NASDAQ gained, but not much. It says it's a very negative statement. Would you be unhappy if you had NASDAQ stocks or NASDAQ index funds and market it gained a little bit? You wouldn't be unhappy, right? Unless you were greedy. Right? So that's the value of pre-training it. So now I'm going to move a little bit faster, but before I do that, let me take questions from the chat. Zay, could you mention what are the questions?
Actually, the question was on Slack, not on chat.
Oh, on Slack. And what are they?
Okay. Dilip asked. Okay, actually, Kashish wanted to show the demo.
Kashish.
Yeah.
All right, Kashish. By the way, I'm not muting anybody from my side unless, it's creating a negative feedback. So please unmute yourself and share your screen.
And then another question.
Can you hear me?
Adding a layer of a local data fit in the architecture of the transformer.
How does a
pre-trained model?
Yeah, so you have a pre-trained model. Remember, it can do a generic set of tasks or maybe pre-trained for your, when you give it more data, it is like running a few more epochs of training. What do you do when you train a transformer or a neural network? You take data, training data, and you run a few epochs through it. But nothing prevents you from adding one more epoch at the end, a few more epochs at the end with a different set of training data. So what it will do, it will shift the weights. The weights are going to readjust and it will adapt to this, but it will not go through radical transformation in the sense that there will be minor adaptations for this. Okay, what's the next question?
Can you see my screen?
Okay, let's look at Kashish's demo.
Can you hear me?
Kashish, can you speak up? Try to say, because I feel that, is there anybody else who is having this problem remotely? They can't speak? Or did I do something here?
Can someone on Zoom hear me?
Oh, I reduced my volume. Sorry.
Hello?
Yes, we were trying to.
Yeah?
Yes, Kashish, we can hear you. I think it's Asif's.
Okay,
side.
can Asif hear me? Uh-oh. Okay, I can't hear
Asif,
Asif.
you're on mute now. Asif, you're on mute.
All right, now we should be having both ways.
Okay, perfect. Okay, so I ended up using the corpus and like the data set that you had given. So I got it to work in Streamit. It took a lot of time. There was a lot of issues on Mac. So I did all the ones that you had shown us. So for a text to image, that can just be anything. So it generates that, and I set k equal to 5, so it showcases just 5 images, but you can always change that.
You're right.
To see more. And then even if you were to do something else, it works. So that's the text to image search, and then
Try a lion on the mountain.
okay.
Pretty close.
It got lion, it got mountain, but the first one it got.
Well, a bit of exaggeration to call it a mountain, but yes.
Definitely. Okay, so that was text to image, and then my text file to text, I ended up uploading a text file of the book, The Power of Now, just to see, but I need to do some transformations to the text file because when I run some text, so this book is, if what's in, I'll just do something good for you, something like that. Because the file of the text was a little weird, it's not getting the complete sentences, so I just need to do a little bit of data cleaning, and I think it'll be able to, yeah, so it's getting some of the headings, and it's not completing the sentence because the line is breaking in the text file. So I think I need to do some data cleaning, and I think this will work properly after I clean the file.
Yes, I also think so. See, data preparation is a large part of it. When you take a book, a text version of a book,
yeah,
you have to know that there's a lot of things to subtract or elide from it. And much of the data preparation, when you deal with the, like for example, Gutenberg, which has the largest collection of free books, they give you the text file. First, like 5,000 words are just the copyrights and the preface and all of that table of content. You have to sort of eliminate that. And
yeah,
one way you could do it is, it's bringing up the chapter headings.
right, it is.
You could use the regular expression wherever you see everything in caps.
Regex, okay, yeah.
Yes.
Okay, good idea. I'll definitely add that right during the break. So yeah, I just have to work on the data cleaning, but I think this is working fine once I'm able to get that. Then
Eckhart Tolle's book, isn't it? The Power.
Yeah, that's right. That's right. And then for image to image, just from what we had done in class, similar to that. Oh wait, let me do a different picture actually. Okay, maybe of the moon.
Oh, it comes up with lots of pictures of the moon.
Yeah, so it's from that same data set you would use with the 25K unsplash file.
Nice, very good. This is good.
And yeah, this text one, I didn't use the ANN one yet, but I'll add that in. I was just trying to get Streamlit to work, so it was taking some time. But yeah, thank you.
No, this is very good. This is very good work, Kashish. Sorry, I had muted down my voice and then I couldn't hear it.
No worries. Thank you.
All right. Any other questions, guys, on the
12:25 p.m.
Any more questions, right?
No,
No, that's it. That is it. Okay, so what we will do now is move a little bit faster now that we know this example.
Hey, Asif, I think Haripriya had a question for you.
Go ahead. Haripriya has a question.
Sometime back.
Oh, Haripriya, are you there? I think she stepped out.
Okay. Yeah, maybe she's stepped out.
Okay. So, guys, you now know that we can do things. What can we do? Let me show you some examples that may, you may say sentence analysis, blah, but if you have sentence analysis, you can, I'll give you a homework. This is your homework. Play with the Hugging Faces text classifier. How tough will it be? One word change. Instead of sentiment analysis, your text will, your task will say classifier, right? And then you would give it the labels and whatnot, right? So do that. Homework is use the Hugging Face text classifier. That is a little, very short homework. Do it on your own. But I wanted to show you something that is a little bit more impressive, which is this notion that you could.
We're seeing your Slack.
You're seeing my, oh my goodness. Okay. Hopefully this is better.
Yeah.
Yeah. So these are called the zero-shot classifiers. I explained it to you, right? Generally, you tend to take slightly bigger models to make it work. They have to have learned a lot, generally. And the bigger the model, the better they tend to get. So I'm saying there are 3 texts that I'll give. And you have to classify the 3 sentences into one of the 3 labels: economics, politics, science. You could give more sentences, guys. If you can think of other sentences, I'm really happy to add. So, you see the magical thing. Not only are you giving it the input, you are specifying the target space. You normally don't do that with a model classifier at inference time. That's non-standard. So you say, how in the world? You seem to be doing both training, or no training, directly inference. That's why the word zero shot. Yeah. But can it do that? It turns out that it does that. So it says, this is a fear. I think there should have been, there is a fear, but okay. This is a fear that we may be heading into a global recession in 2023. So it says it's about economics and not much about science or politics. Would you agree? Right. The next one I said, a free and fair voting and voter participation is the foundation of democracy. It says politics. Then I said, heavy objects deform the space-time fabric around them, leading to the gravitational force. Right? So that is obviously Einstein's theory of relativity, that the heavier you are, the more you distort the space-time around you. And then things that pass by, they tend to go through the bump, that deformed space, and it looks as though you are attracting it. Right? You're pulling it. So, well, science.
Hey, Asif, you're attracting all of us to you.
Yeah, I can see I'm pretty heavyweight. Well, I'm trying to be lighter, create less deformations in space-time. All right. So another homework is try to replace it with other models, guys. With Hugging Face, you have to play. People have created an ecosystem of so many models. Do you notice how many models are there? 166,000, and every day it keeps on increasing. Right? We'll do a few more examples, guys. I hope this was illustrative. The fourth one is text generation. Let's try text generation or continuation, you can say. So what is the task? Text generation is the task. I say the happy cow jumped over the moon. And the output, by default, the default model produces the output that says, the happy cow jumped over the moon. As we approach the place of our meeting, the young and beautiful woman stepped forward and asked me, call me to my, I don't know what junk it produced. Okay, this seems to have produced some junk. Then what happens if you use different models explicitly, GPT-2, Distill GPT, and Facebook? Facebook Opt is a more recent model. Let's give it a quote to continue beyond the code. Now, anybody remembers this quote? Anybody has seen this before? It's on the wall.
On the wall, back of the room.
Yeah, it's in the wall, in the back of the room. So you ask it to go generate, I don't know, this one is almost offensive, what it produced. So this is the risk, guys, you know. It is a risk with text generation. You don't know, it may produce socially offensive statements. And GPT-2 says, education is not the filling of a pail, but the lighting of a fire. Then it goes into that, as well as the fact that the New York Times wrote about the event. There's also an online petition of 1,000 signatures. And even if you disagree with the reporting, then please share. Is it at all relevant? It's nonsense, right? That was GPT-2, guys. GPT-3 was already better, and GPT-4 is what your chat GPT is, right? So how much difference has happened? Distilbert says, but you could even imagine a world for an ordinary person at least a year and a half from where our lives are not in any way threatened or destructive, in that it was a good time to let us know that we are in peace. Even if you could understand it, it doesn't make sense, right? It has no relationship to that. What does Facebook do, Opt model do? It somehow brings in Mark Twain, right? The first thing I learned in kindergarten is that the world is a big place. The second thing I learned was that the world is a big place, right?
Whose quote is that?
Mark Twain, possibly. It says so.
No, like the first one.
It actually belongs to a Greek philosopher named Plutarch.
Okay.
But it is wrongly attributed to W.B. Yeats of England.
Okay.
Y.B. Yeats, not W. Y.B. Yeats of England. Most people think it's Yeats who said it, but actually it was Plutarch of ancient Greece who said it. So what is the state of the art on these topics? Now comes, and this is the problem, guys. We are facing a dilemma. These big models, people are claiming you can't put it on your laptop. You say, well, I have a big laptop, a big machine. Then also they're hesitant. GPT-3 can now be accessed, I suppose it's been. But GPT 3.54, etc., they don't give it to you. So I'm looking at some of the state-of-the-art models. Chat GPT, Cloud is from Anthropic. Chat GPT is from, of course, OpenAI. Ask the same question. I give them. I said, generate more text to follow the sentence. Right? This is the prompt I give. So Chat GPT, which is literally GPT-4 continue. In a sense, there's more to it. But you know, it's not just that. Remember, now reinforcement learning has kicked in and other technologies have kicked in. It says, in order to truly light a fire in a student's mind, educator must be willing to take risks and experiment with new teaching methods. This would involve incorporating. It looks far more relevant, isn't it? And ultimately, it goes on to explain, ultimately, the goal of education should not be to simply fill a student's head with facts and figures, but to help them become passionate, engaged learners who are equipped with the skill and knowledge they need to succeed in an ever-changing world. By lighting the fire of curiosity and imagination within each student, educators can help them unlock their full potential and become lifelong learners who are eager to explore and discover new things. Right?
So Chat GPT is just, it's like a sentence transformer. If you give some text and you give you.
It's a pure text to text. Yeah, it's a text.
Totally more advanced. Like you give an image, give you an image. And
yeah, it depends on the task. It was never trained for the task of images. It was trained only for text to text.
now I'm giving a comment that they're trained better than Chat GPT. So we can give an image and we can get another image.
Yeah.
So we can.
Yeah, no, see, that brings in this whole question of chains of things. What you can do is Chat GPT can become just one member of a long chain of things you can do. So for example, you could be taking spoken audio, converting it to text, asking Chat GPT to convert it into a sonnet, Excuse me. That's popcorn doing it. Creating a sonnet and have another transformer convert it into audio, into a human voice of a child reciting that poem. You see how you can do that? So you can create long chains of things.
But to like incorporate ChatGPT, you have to use the API.
You have to add the API in between. So actually, most of the startups that are happening around ChatGPT is exactly that. They're saying what chains can we form and do fun stuff with it. Right?
They're not to use the model. So
They have.
That's what Elon Musk was complaining.
Oh, me too. Now they become greedy. They're anything but open.
Yeah.
Right?
Because Microsoft is coming.
I think it's also this, it's a good way to make money without having to publicize anything.
Yeah.
Because everyone's using ChatGPT. It's like one of the most popular ones. Like everyone uses it in school, college, work, right? So it's like for them, they're thinking, how can I continue to make money? That's why they have that whole like.
Absolutely, it's a financial model.
Yes,
thing,
it's
yes,
a
I'm sure. There's also, I can't help thinking, it's a bit of a Microsoft thing. 20 years ago, supposedly their strategies, I don't know whether it's fair or not. It used to be adopt, extend, extinguish.
Yeah.
Right? They would adopt a technology, then create their own extension that nobody else could have, and then finally just completely take over. Right? And if needed.
Asif, it's sad that they are monetizing it for their own benefit, and they're willing to kind of extend that model, but then keep that information to themselves and not share it with the world so that nobody else is able to monetize. So with the OpenAI, they've quickly realized that other people are also monetizing, maybe not as big as a piece of the pie like they do, but able to monetize, and they don't want that, which is ridiculous.
Yeah. See, the community practice has been research output should be open. Applications and products built with it should be monetized. But this time, they have sort of crossed the line. They are saying research output itself should be, we should monetize because so many applications can be built into it. We see a possibility.
Yeah, they are not sure the GPT-4 paper, how many parameters.
Nothing.
Just
It's not a paper, it's like a white paper.
yeah, that's all.
Yeah.
We only say how it can do. That's all.
It's a long bragging rights. That's it. So then, not many of you know, there's a company, actually Shalini here in our audience works there, a wonderful company called Anthropic. Some of the deepest thinkers a few of the deepest thinkers that I know about neural networks, I noticed, and I was surprised that they have all moved to Anthropic. Pretty good guys, deep guys.
Funded.
Google funded, yes, Google funded. So, so they have their own chatbot. I put it to that, and I would strongly suggest you guys go get an account at Cloud. So here is what it said. In my view, it is shorter, but much more sort of relevant. Look at the continuation, it says. Education is not the filling of a pail with the lighting of a fire. A teacher does not simply pour information into students' minds to be stored and retrieved later. Real education sparks an inner passion for learning and curiosity of the world. Right? That explains it in a way. So it follows the style. Say in English, there are many styles that you write paragraph. Like one of the styles is that you start with the sentence, the thesis, and the rest of the paragraph amplifies that thesis or elaborates on it, which is the way it took. It fuels a lifelong love of discovery and blah, blah. I leave it to you folks to ponder over lunch if I have succeeded in being a skillful teacher. But with that.
Hey, Asif, my comment about our attraction to you was not about your true mass, but the massive knowledge that you have. So,
yeah.
And we want that to increase, not decrease.
I know, Dilip. It's someone friends, don't worry. It's all for fun.
Hey, but Asif, your teaching is amazing in a sense. got flipped classrooms where, you know, they ask people to go just look at the PowerPoints and do like a practical session. But you're doing the combination, right? Doing the theory and the practical stuff.
Yeah.
Great teaching us.
Oh, thank you. Thank you. This is my motto, actually. That's why it's there on the support vectors wall. I would love to be remembered as a person who lit a fire, who created, you know, at the end of our life, you know, we have built so many products, Dilip, you and I, as classmates now, 30 years of scientific and engineering training and work later. We have built all the great, you know, products that we wanted to build. Now is the time to build the next generation. Who will go and build the next products? I believe in that. So thank you for saying that. So guys, you see the possibilities and the limitations. Never, and by the way, this was very interesting. I had not noticed it, that the first one produced text that is actually objectionable. It's quite objectionable. It is so degrading for women.
Hey, Asif, do we have this Jupyter notebook to modify?
Yes, I'm giving my apologies. Like I said, let me show all of this. Within a minute of our breaking for lunch, it will all be on Slack.
Okay, thanks.
Within a minute. I should have posted it before the class. I apologize, I didn't do that. But I'm on my last one, guys. Bear with me. But this one, okay, not the last, second last one. Something called named entity recognition. See, what happens is, suppose you get a lot of text and you have to say, who are all the people mentioned in the text? That's a tough problem. You have to inspect every word and say, is it a person? And then do it. So let us see what it does. That technology is called named entity recognition. Person, place, location, entity, like a World Health Organization or something, organization. These are the things that it extracts from text. And it has been getting surprisingly good. One of the use that I put it to in a previous project is, I had to do data anonymization for very sensitive data. I had to pass people's performance reviews. You can imagine there's nothing more sensitive than performance reviews. And surely, as an engineer myself, I didn't want to see what the CEO wrote as performance review for the CTO, who was my boss, right? So, but I still, the whole NLP, everybody's text had to go through some NLP process, some task. Right? So the whole thing was nuclear, because if there was even the slightest leak of personally identifiable information or this sensitive information, I was like, pretty much we would have lost our jobs, right? Because you had to be extra careful when you deal with data that is so radioactive. So getting PII out of text fields is easy. Make sure names are gone, emails are gone, this data gone. But when you talk of anonymity, you talk of things like many things. There's L diversity and what is that? K anonymity. Like, are there at least K people who are exactly like this, so that you don't know which of these K people it is, and K should be sufficiently large, right? So, for example, if you find that somebody doesn't have a boss, somebody doesn't have a performance review at all, ever, what can you conclude?
Not doing any work.
CEO, right? So you lose K anonymity there. So things like that, L diversity. So those things you could enforce. But then the problem was text, because you're dealing with text and people tend to write people's names. Peter was good at this and Peter has this to do. That's a style of writing performance review, just to emphasize that you know who you're talking about. Yeah. You need to remove Peter from the equation. So what I did is named entity resolution to mask that. Before, it's a pre-processing step before it goes into the algorithm. So here we go. Peter Maxwell went to San Francisco. By the way, occasionally, if you see an article written by Peter Maxwell, you can remember it's a code word. It's written by yours truly. It's one of the pen names I use sometimes. The other is ripe apricots. Some of you know about the ripe apricots, isn't it? So so presented his paper at the Moscone Center. So look at this. What are the proper nouns here? Or the named entities? Peter Maxwell is one. San Francisco is a location, right? At the Moscone is it. Let's see if it got it right. It says the first one it found is Peter. And it is pretty sure it is a person, right? Second one, Maxwell, also it's pretty sure is a person. Then it says there is a word, San. It's about location. Then Francisco is also about location. And MU, it sort of seems to have gotten wrong. It says it's a location, Moscone, because it broke Moscone into two parts. And the Moscone part, no, San Francisco, Moscow, Moscow. Why did, so I don't know, Moscow, it has also marked as an organization. It has marked as an organization. So what can you infer sometimes? Because it uses word pieces, right? Remember I talked about word pieces?
Moscone, isn't this Moscone and O?
Oh, that's the reason. Maybe that is the reason. I got it wrong. Thank you. Moscone. I stand corrected. Let's do it again then. So it will take a little bit to happen, but you can see. So while this is happening, let's go and look at something which I would like to end today with. So guys, today is Hugging Faces Baby Kindergarten Day, right? So these are simple exercises. The next time will be Hugging Faces Deep Dive Day. All right. And then we'll be done with Hugging Faces. And the last 4 sessions will give to fairly deep things. Last 4 days will give to fairly deep things. Recently, there came a paper that completely, like 2 papers that in multimodal learning that were fairly transformative. One of them was CLIP. You have encountered CLIP. We used it in search. What it did is it could translate an image into caption, into text. And they call it zero-shot learning, but there's a caveat to it. They don't need label data simply because they scrape only those images of the web that had the caption written below it, right? And so they actually had label data by scraping the web. But it was zero-shot in the sense that they didn't have to throw a bunch of, people and ask them to label it. But then right after that came another paper, which was DAL-E. I suppose it was a word game on Wall-E. Remember Wall-E movie? Right? So it was DAL-E. And that paper starts with, and we'll discuss that paper in this course, not today perhaps, but maybe today itself, the architecture of that. What it does is, you give it a textual prompt, and it will render an image for it, however impossible that image may be. So, for example, the paper asked for chair designed like an avocado. Now, to my knowledge, no furniture manufacturer makes furnitures shaped like an avocado fruit, right? And yet it made perfectly good chair designs like an avocado. And we can look at the images. Likewise, it created some daikon on a walk. Right? I believe daikon in Hindi, we call it the muli, right? On a walk. And walking a dog. So imagine a daikon walking a dog, right? It perfectly nicely rendered a daikon walking. You give it you just say a billboard. Suppose you have a company, right? And you just started a company like I did, Support Vectors. But you want to create an impressive image for your website, so you have to look big, right? So, some people tell me that to be successful, you have to look successful, right? So what you do is, you give it a prompt, a high-rise glass building with the logo, Support Vectors. And lo and behold, it will create a beautiful building, impressive looking, and put Support Vectors as a logo on it.
This is in DALL-E or?
In DALL-E. So DALL-E caught people's imaginations, and a lot of people started doing it. Its open source versions came in, and there was rapid progress. One of the key progress elements was stable diffusion, an approach which was actually radically different from DALL-E. Then OpenAI pretty much adopted stable diffusion and made some more training on it and some adaptations, further work on it, and they call it DALL-E 2, a huge marketing scoop, right? And the stable diffusion people were really, right? So anyway, the fact is, there's a whole bunch of architectures, and now there's look into things, the recent works like ControlNet, etc. It makes it even more fine-tuned on the prompts, respond to your prompts better. And there are entire companies like Midjourney is one of them, that for a paid service, you can give prompts and generate images. And things came to pass that one guy, I think in Wisconsin, Madison or somewhere there was an art competition, and great artists would bring they would bring their big paintings, and his painting was submitted. And the critics absolutely raved about it. They're so great and this and that. Look how finely the details are and how well masterstroke there is in doing this. Everyone agreed this is the best, and it got the first prize. And then it turned out that it was a transformer that did it. But then starts a controversy, a big controversy in the art world. Is it legitimate or not? Is it creative work? He claims it is. Instead of being creative with the brush, which is now ancient, he had to work really, really, really hard creating the right prompts. It's not that easy to create that. We had to slog for days and days and days to create just the right prompt to create this beautiful painting, to make computer produce this painting, right? So it goes back to the debate, like if you create a picture using Photoshop graphic, right? Is it art or not? Today we agree that it is art, it's graphic art. It's not photograph. Photograph, we expect some degree of originality, even though there also a little bit of contrast and etc. we allow for. But we don't allow for putting a sunrise behind a hill when there was no sunrise. That's not a photograph anymore. Right? So that was graphic art, we acknowledge. So there's a big debate now because all the actual artists are frightened because they feel that now AI is going to eat their lunch.
No, it's also trained on their work.
And it is trained on their work, which is a big copyright issue. Thank you for bringing that up. The big thing is transformers are mathematical objects. They need a lot of training. These things have soaked into the work of 2,000 years of art, let's say, and 2,000 years of literature. And that is why they're doing it. So in a way, they are sitting on the shoulders of work that's copyrighted and belongs to perhaps 100 million people, right? So therefore, who should they pay royalty to? To 100 million people, right? So what it means is that the legal framework, see, in the Western world, there has been the framework of patents and copyrights. It has been excellent. Part of the reason there is so much innovation in the West is because of the patent and the copyright laws. You have an incentive to innovate, because your innovation is protected and you get rewarded for it. But if your innovations are not protected and your creative work is not protected, you lose the motivation. You can see countries in which copyrights are not respected are very uncreative countries. So it's a big debate, actually. And so now, with that background, let's look at an example. So there's some libraries you have to install. I gave simple prompts. One of them is, and this is literally an example that was online. Image of a squirrel in Picasso style. Picasso was a great cubism, right? In a cubist style. Does it look like a squirrel in a Picasso style? Like Picasso would have done this, right? So play with it, guys. Say in the impressionistic style, right? Give something in the impressionistic style, etc. You'll be surprised what wonderful art exists on the web. And what they do is, a lot of the people are monetizing it like this. They will create this service on the web, but it costs them because it is compute resources. What they do is they'll let you make the image free. They'll give you a low resolution version, but they'll say if you need a high resolution printout, right? or print on a canvas. We are giving you print on canvas or print on paper or print on metal, and the markup is huge.
Maybe you can do NFTs also.
NFTs also, yeah, that's a very interesting thought. Yes, you could do that. So the other one I said, which I thought would be hard. I said monkey on a boat in a stormy sea, right? And it seems to have done that. Would you agree that this is a plausible picture of a monkey on a boat in a stormy sea?
Yes, ask Mona Lisa by Monet.
No, go ahead.
Can we ask you to draw Mona Lisa but by Monet, not Da Vinci?
Oh, yes, yes, you could do that. You could do all of that.
It should be fun to see. So
Yeah.
put flat background.
Yeah. No, go ahead.
This is like
Text to image. Yeah, text to image. Look at this code. What did we do? We said 3 lines. Get a model.
Yeah.
You give it a text, and it produces an image. All the next 2 lines are meaningless because I'm just saving the image and displaying it. You see how easy it is?
So this is on generative. Not
Generative,
search.
yeah.
Not the search, because the first one was search.
Yeah, generative AI. So we are now moving into generative AI with this. Harni, go ahead.
Asif?
Yeah, go ahead.
Sorry.
Yeah.
Yes, please go ahead, Hardini. I'll ask later. Please go ahead.
I think it was you,
Okay.
Go ahead.
So here you're importing from diffusers, import diffuser pipeline. That is also coming from Hugging Face?
It is all from Hugging Face.
Okay.
Everything is from Hugging Face.
Got it.
So diffuser library is part of the Hugging Face. So people have uploaded all their libraries there, right? Somebody has gone so far as to take really good scikit-learn models and post it to Hugging Faces now.
There's a bit of an ethics and play here, right? Like
AI has a huge ethical debate. Yeah, absolutely right. Yeah,
because human
the simple classifier, the simple things, work through it through lunch, take an hour lunch and 1 hour to do the lab, because afternoon will be theory. Right? And I'm posting all of these notebooks before I forget onto Slack. And I'll pause the recording. So welcome back, guys, after lunch. Now we are starting the second session of this Saturday, April 1st. We are going to, I missed a lab. So I'll do one final lab. And after that, we'll go into the into the sentence bird architecture. So where am I? Share. No, I'm sharing the wrong thing. New share. It's hopeless. New share. Yes, much better. Folks, are you seeing my screen?
Yes. Do you want to record this? You're recording.
Oh, yes, I am recording. And I'll make sure it is, yes, it is being recorded. All right, folks, I missed something which I would like to cover. It is, we can do one interesting thing with transformers that may not have occurred to you. You can give it a picture. Let's say a picture like this. And now you can ask, what is it? Right. So then when it sees a picture like this, it will come up with and say it's a snow leopard. Right. So it's somewhat very close to the search problem we did last time, find other pictures similar to it. And then, but in this particular case, it comes back with the name of the object that it thinks it is with probability. So it's very, very, it's pretty clear that it's a snow leopard as far as it can make out. I suppose the snow is a giveaway. Right. But you can do more than that. And here's, I think, where when you first see it, it is impressive. Now, the second part, you may or may not be able to run on your machine, based on whether you have Ubuntu or not. I know that it works certainly on Ubuntu. And these are the instructions for installing the optical character recognition stuff in Ubuntu. Similar instructions are available for other operating systems. And I'll put a link for that. But for now, just look at this picture. Do you see an invoice here? It's a scanned image of an invoice. And you could just, and pretty long invoice actually, thank you and all of that. And you ask this question, first question you ask, what is the invoice number? Right? And it comes to the answer that it is US 001. Let's see if that is true.
Yes.
It is that right here, US 001. Another question, what is the invoice date? Invoice date here comes out to this, which doesn't look like a date. Now, can you guess what happened? Look at the date here, invoice date.
Yeah, just converted it.
Yeah, the slashes got interpreted as 1, right? So there's a little imperfection here, but so you could use a slightly more powerful optical character recognition thing because it's an OCR thing. It didn't get the slash right. Yeah. You could ask, what is it built for? Actually, it should be who is it built for? Who is it built for? And it says it's built, sorry, who is it built to? It is built to John Smith. Right? And likewise, you can ask other questions. Right? What is the amount charged for labor? And so on and so forth. And it will answer. I don't know, like I don't know if you guys were aware that these things can be done.
We are captive. The document that we have is captive. Did a lot of this OCR.
Okay.
Now with this algorithm, it's doing it all free.
Yes.
It's taking the entire product.
Yeah. No, but see, there's a sort of an arbitrage thing, right? The information propagation is slow. Most people, they don't know that the world has changed, right? So all those softwares are still doing pretty well.
No one knows this.
Yeah.
So this is also like using transformers?
It's transformers all the way, right? Remember, this entire course is transformers, right?
But what exactly you did here? We ran this OCR, we transferred this image into text.
Into text. And then
on that text,
yeah.
how do we get multiple documents out of that one image?
Yeah. So what it does is there are two aspects to it. One is that it's acting on the image. Like, for example, this leopard, right? When you say, what is this? Yeah. This is literally a transform, somewhat like clip architecture. It is basically trying to tell you what is the thing that you can most closely associate with this. Right? So that is pure transformer. This image is a little bit more complex and we have to study it a bit. See, this Tesseract OCR is an OCR library. So it is certainly doing some text extraction, but you have to know where the text extraction is. Are we taking out the entire region? But you can't do that because if you do the text extraction, you don't know which value goes where, right? In the picture. So suppose you say, right, the word, who served the invoice? Who served the invoice? Let's try that and we'll see. Who served? Right? And you notice that it isn't that easy. It isn't just OCR because it has figured out that this is the company. So it's able to semantically place meanings to their locations in the image.
So this is also doing like it's creating the tensors also, yeah?
Everything. Yeah. So see, guys, when you see this, these are just some examples. Today were the easy examples. Next time will be more code.
So this is open source, is that?
Everything, of course. I'm not teaching you anything that's closed source.
There was another product where you could scan invoices and you create an Excel sheet with all this information.
Oh, easy. See, OCR, the standard OCR has been there for a long time with little value adds. If you know semantically, this is this, this is this, this is this, you can do that. But now we are going to the next level.
Because before it would like put Bill 2 and say
Yeah.
John Smith. So it will kind of do that mapping, but this is a little bit more.
Yeah. You can literally just scan through, like run through 200 documents and say, okay, what is the sum total of all the amounts?
Wow. You can do it.
We can. All you have to do is batch it. I mean, write that little bit. You get, it is not creating unnecessary data. It's just giving you one answer, 15406, right? And then you can feed it to the next one. You can keep accumulating it.
You can do the problems, all of the examination things. The professors in England, they used to take marks and then
Yeah.
ask the kids and to kind of go back.
Yeah. A previous TA of this class, somebody who was a part of the teaching staff, Kunal Lal, some of you may remember Kunal. So he's actually doing a startup exactly like this for a DocuComb. What he does is when people come to the US immigrant, there's a lot of legal paperwork. So all of these documents exist. And so all you have to do is take pictures of all of them. They don't even have to be straight aligned or whatever, just snapshots, and upload the whole directory of pictures. Don't even have to tell them this is the passport, this is the visa, this is this form, this is that form. And immediately it extracts without being told what is what and which field is where, because it differs from country and so on and so forth. It immediately extracts everything and creates a nice dashboard for you. Right? Of all you, it even knows which document it is. Okay. So I mean, people are actually forming companies on that now. Yeah. So, all right, this is a bit fun day. What are the things that transformers can do? But now I will change track and go into the into understanding. So in theory, we are one sort of lecture behind. We have finished sentence BERT, semantic search, and so forth. And I mentioned that behind it are some crucial ideas. One of the big ideas is the sentence BERT idea. Yeah. So I would like to do this paper for the remainder of the time in some detail, right? It's a very easy, well, relatively easy paper as papers go. So let me start on it. This paper came out in August 2019. Right? So in a way, you can say that this technology has been around for almost 4 years. Right? And so we'll go over it now carefully. Let me get rid of my keyboard. Yeah. And I will convert this screen to my writing, decrease it a little. Yes. So let's look at the first thing. It says in the abstract that Bert and Roberta is a variant of Bert, have set a new state-of-the-art performance on sentence pair regression tasks, like semantic textual similarity, like how similar are two sentences. You can do that. Why is it a regression task? Because similarity is a number. When something predicts a number, a model predicts a number, it's a regression task, isn't it? By definition. So this thing is often abbreviated as performance on, oops, sorry. What did I just do? Sorry, page up. Yeah, and this. So this is the important thing, performance, state-of-the-art performance, like this. So remember, I was saying that the papers these days are very metrics-driven, state-of-the-art. It starts literally with in the second line itself, the SOTA is there. So the problem with these networks is that, suppose, as they say, so what he's saying is that finding this requires 50 million inferences. So if you want to find, suppose you have 10,000 statements, and you want to sort sentence pairs by similarity, sentence similarity. So it's all right. You can use BERT regression tasks for finding similarity. And you have some way to do that. You do it. Now, how many pair comparisons will you have to do to find the 5 closest pairs, let's say, or something like that? You'll have to find all combinations and sort them. Now, how many combinations there are? So that's a bit of combinatorics, right? So suppose there are n documents, right? Now, each document has to be compared to the other n-1 document, right? So you have to multiply it by n-1. And now the distance between A and B and A should be the same. A similarity number should be the same. So you don't have to do twice the comparison. You just have to do half of it. So this, in other words, this is n choose 2. Now, when you do 10K, you realize that for n is equal to 10K, these comparisons, pairs, comparisons are 10, right? 1,000 times, well, 999, if you want to put it this way, divided by 2. Isn't it? And that comes to, well, this one, forget n-1, it's almost 10K. So 10K times 10K is 100 million. 100 million divided by 2 is 50 million. So at that time, the hardware used to be V100, was very expensive hardware, server like data center class and so forth. And you would pay massive amounts to rent it or use it or buy it. On that, it took 65 hours. 65 hours to train. But now, what if you, on the other hand, took one query? So let's say that you want to create a search engine. So you have a query sentence and you want to find the nearest match in the document. So you have to now go and compare to 10,000 entries. So you say, well, that should be fast, right? Well, it turns out that that wasn't fast either, because that would take you, again, all things said and done, to answer a question would take you 50 hours, right? Pairwise comparison with BERT, answering a single query would take 50 hours. None of these are practical. No, these are not practical. So people knew, as I said, that BERT is a great cross encoder, can give you good answers, but it is way, way too expensive. So, and in a way, this, as I read through this statement, it is a review of what you have already learned, but what I've already been talking about, but we talk about it again. Now, where did my mouse go? Sorry. Here it is. Now, let's go here. Also, this sort of task, right? You can't use it for clustering and for things like that, because all it is doing is a pairwise comparisons and things like that. So you can't do that. And through, I mean, he's just saying what are all the problems that you can solve. And here, there is such a thing in neural architectures, those of you who took the deep learning workshop know, called Siamese network. Now, Siamese networks are exactly designed for this, right? What do they do? So let's take a little primer on Siamese network. What a Siamese network would be, irrespective of what architecture you use, you pass a data through X, it produces some hidden representation of X, right? You pass Y through it, actually it's the same copy. You don't, even though I'm making it look as though it's different, you pass it Y, and what you do is HY, right? Actually, let me just say that XP, I think let me call it the positive P for a reason, something P, and same thing, a negative sample, and I'll explain what it means. It will create a H negative sample data. So imagine that it goes through some neural network, doesn't have to be transformers, any neural network, it will create a hidden representation and embedding out of it. Right? once it produces an embedding, now comes what can Siamese networks do? What Siamese networks can do is that you can now train a network in such a way, you can create a loss function, this is a loss function in such a way that if P is close to X and N is unrelated to X, then the distance, some distance measure of X and P should be less than the distance measure from X and N. Would you agree? Isn't it? So basically what we are saying is using these two, some distance of Hx, Hp, it should be substantially less than distance from Hx, H negative. That's why this is called the positive sample. This is called the negative sample. Are we together? And this can be done. What you do is, this is often called Siamese network. These words you'll see together: Siamese network, triplets, and triplets to train it. Because how do you train these things? You give it not pair, but you train it with. You take a reference image. So, for example, think of image people, right? So you take a picture of a dog, a golden retriever, and then you put another picture of a golden retriever. That's a positive sample. And then you put a picture of a mountain. It's a negative image. So you create a data set with whatever number of rows you have, let's say 10,000 rows, 10,000 training data of positive, negative, and reference pictures. The first one is called the reference image, right? And the point is, P should be close to, in the embedding space. Would you agree? That's the only way it will make sense. That positive should be close to X, negative should be far away. Okay? And if we can do that, if we can create a loss function, right, that leverages this, and typically in this thing is the loss function is, and we'll get to more precise definitions. Let me just call it Hx, Hp minus the Hx, H negative plus epsilon. You say that the loss between them can, and the max of it, like the distances, let's say that, why will I say max? So let's parse it this way. First, let's look at this. You want this to be positive, isn't it? But what happens in the beginning when you're training, in the beginning of your training, your positive will go randomly somewhere compared X. Suppose X is here, P is somewhere, and N is somewhere. It is easily possible that the distance to N is closer than the distance to P. So your value will be negative. But you need a positive loss value to be able to gradient descent. Otherwise, what will happen? If you try to minimize a function which is negative, it will run off to minus infinity, right? You don't want that. So what you do is you put a threshold at 0. Not only put a threshold at 0, you do even better. You say that if the distance, so let us say that negative is less than positive distance. Sorry, positive distance is, actually, did I write it the other way around? The negative distance should be more, yeah, the negative distance should be more than the positive distance, right? So max of that, right? Or positive minus, okay, we'll see. I think I'm screwing up the formula. It's here. Let me see. I thought it was common sense, yeah. Similarity, oh, no. I'm using distance and they are using a similarity measure. So in my distance term, this is correct. The distance of negative and positive. And the converse of distance is similarity. So then you would say, some people write it with distance, some write it with similarity. So then you would say that you can say similarity of X minus similarity to the positive sample, right? Minus similarity, and then the size of this similarity and the size of negative similarity, negative sample, right? And you put a minimum threshold of epsilon that they should be at least this much apart. right? That is the thing. It's just a mathematical way. You can twiddle around with it, and you realize that yes, this is what we want to. This is here, right? So, do we agree that this formula makes sense? Where are we? Ultimately, if you have a triplet, you want to make sure, right, that similarity, right, is closer. There's not to the positive samples. Yes, right. So, and these are sentence embeddings. So the distances are like this. Now comes the question. So this explains this kind of image. Do you see that there are two networks? This is one, supposedly. So in Siamese network, right, they make it appear that there are two networks, but actually there are no two networks. It's the same network. The way they say in the languages or in this paper, it says you take two networks with the same shared weights. Shared weight means they are the same network. You first pass in A, then you pass in B, you pass in X, then you pass in the positive instance, and then you pass in the negative instance, right? Or you batch it all three, and you get the results. So then, now let me explain the pooling part here. What is this pooling? See, what happens is, you remember that in a sentence BERT, you pass in the words, right? Token T1, T2, and the embeddings. Ultimately, what comes out? Output hidden 1, H2, HN, right? So there are multiple ways, and then there is a special hinting for the HCLS. So the classifier, remember the initial token, special token. So some people, what they do is that they use, you need to pass in, suppose you write a classifier whether two sentences are similar or not, or something like that during the training process. You need to pass in a vector, but which vector? So you can just give that special output for that, the CLS token. Some people do that. Or some people, what they will do is they'll take the average of all the vectors, the output vectors, right? So the average is called mean pooling. You take the mean of all the vectors, average. Generally, this paper says that they experimented and they found that mean pooling works better. Right? So they use mean pooling, and that vector goes into the basic. The rest of it is easy, softmax classifier, right? You feed it into, and how do you feed it into it? You take this use pooled vector. So actually, let's say U and V in this are the two. Sentence A becomes U, sentence B becomes V as hidden representations after pooling, average of their pooling. And then what you do is you concatenate, you do something funny. You take U, you put V, and you put U minus V, right? As 3, you concatenate these 3 to create a 3 times as long vector, let's say. And then what you do is you feed it into, because then what will happen? You get the representation for sentence A, representation for sentence B, and a representation for their distance. And you feed that concatenated information into a softmax, and you say, well, classify. Right? And by the way, usually when you do classification, you mean multi-class classification, like one of that. There's a dog, there's a cat, there is a bird, there's something else. When it is 2, then it is implicit that if you have just a binary classifier, softmax could be replaced with a larger stick or something like that if you want.
So even though they are like showing 2 networks here, it's like actually one network.
It's actually one network in which you pass the data. Yeah, you don't even pass data one after the other, because you can batch. You can set it in parallel, you just shoot both of them through. Or in the triplet case, you shoot all 3 of them through. So the problem is, so what problem did it solve? You still are giving it pairs. No, what you do is you're actually taking a training data, which is made up of triplets. Somebody has sat down and said, I'll take this reference image, and this is similar to it, and this is dissimilar to it. So a lot of work has gone in preparing the data, but because it has gone in, you don't have to do pairwise comparisons, 50 million comparisons. Just this Siamese network with its loss function is enough to train it. Are we together? And that's what you do. That is why sentence BERT gets trained very easily. But once it is trained, at inference time, what will you do? Inference time is easy, because you can forget about all of this. All you need to do is the thing that really mattered are these vectors. U and V are the embeddings, isn't it? You have the network that produces U, you have the network, the same network, the BERT plus pooling, all the weights have adjusted themselves, they'll produce you the U and the V. Those are your embedding vectors. And if you want to see if two things, sentences are how similar they are, you just go and do cosine similarity. As simple as that. So what do you save into your database, in your index? The U and V. The vector database saves U and V. Sentence A goes in, sentence B goes in, U and V come out, and you can send them in parallel, in mini batches. Now, there's a bit more to it. See, this kind of thinking is very useful when you try to do what is often called one-shot learning, right? So I'll explain that. See, one example that is often given is, it's a very common example given. You have employees. For a given employee, you may have just one or two pictures in the employee database, HR database, or security database. But the person walks up to a booth with a camera there. Now you need to determine, is this person, let's say that, is this person Mosmi? So how would you train that? Normal classifiers would be trained by giving it lots of examples, Mosmi and everything, every pairwise example it will be trained on. The trouble is you have only one picture of Mosmi to compare to. So you get one shot, right? So what you do is you take some images in the database and you train the Siamese network. You say that, okay, let's say that for this image, Sushinder's image is the reference image, right? I will take another image of Sushinder and say these are positive sample, and every other image of the other employees and call it negative sample. And I will then therefore create lots of triplets. All I need is two images of Sushinder, and then, and sometimes what you do is you just do distortions, right? Or just flipping or something like that to create the other image. And then you pass it to this network and it gets trained. You see that, right?
It's just two images.
Yeah, and in fact, the second image may be just a distortion of the first, right? There's some weird thing of the first. So you can use Siamese because what you can do is you have the positive sample, and therefore all the other n-1 employees, they can help create the negative samples, right? And then you can pass it to the Siamese network, and basically you can have your cake and eat it too. Like typically in a classifier, if you want to tell which animal it is or which employee it is, you would ask for lots of images of the employee, right? Lots of images of a bird, right? But not now. Yeah? That is the power of this Siamese networks. It's a very powerful architecture. I won't go much more into it. Suffice is to say that it is one of the great, powerful architectures. In the deep learning course that you will do, the foundation course, we will go through systematically some of the big architectures, and Siamese architectures is one of them, along with autoencoders and GANs and attentions and all of that, and CNNs and so forth. It's one of the big architectures. We'll do it in considerable detail. But considering that we will do it in considerable detail, I won't go in here. So suppose you have a classifier, go ahead.
Maybe this is becoming more simple. Will this become a problem because there will be more fake pictures?
Oh, yeah. Oh, obviously. But today, so that brings us to GAN, and you'll see that when I talk about GANs in the deep learning course, it is shocking. I'll tell you how it is. At one time, I think it was Lex Friedman who started his AI course in MIT by doing this video. He just showed that we have a special guest, right? But he couldn't be here, so we had to make a video recording to introduce this course. So there was a video of Obama welcoming everybody to the class, right? With completely his mannerisms and everything. And everybody got fooled. It was so photorealistic, absolutely realistic. It captured his accent, it captured his facial expressions and everything. And the whole video was generated. And then the next part he showed is how it was generated. Somebody is speaking, it is going through style transfer, it's going through a process of big Obamaizing this voice, imposing it on the picture, and creating the facial gestures that would go along with it. And for that, to train the data, you need sufficiently long video and audio footage of Obama. Obviously, Obama's permission was taken to do this. That was then. Today, we now know that the state of the art has advanced so much that with just a tiny clip of you, just 1 or 2 pictures of you and tiny clip of you, we can create any fake video, any fake image, you doing whatever, saying whatever, in your voice. Right? Yeah. Come again? No. Yeah, but see, the thing is, people are not realizing how far the field has gone, and it's almost like, you know, you have animals in the forest, and they don't know that there are highways now. Their land has been in, you know, highways have been laid, and so they're suddenly caught dead in the middle of the highway with vehicles going around. That's what is happening to people now. They're believing, see, disinformation is spreading so fast. There used to be a Greek saying that a falsehood goes around the world in the time truth ties its shoelace. Right? That fact has always remained true. Why? Because disinformation is always sensational. Right? So suppose I just told you, let's take an example. Today, it's a normal day, right? I'm there, my wife is there, and actually today happens to be a special day. My daughter's coming, one of my daughters, but let's say it wasn't true. We're just living a normal, and somebody says, hey, as if you know, right, that your daughter has just come home. Would my first reaction be to doubt it? No. So why would somebody say such a thing unless it were true? I would immediately get up and go running home. Yay, my daughter has come. Isn't it? You see that? So the fact that it evokes strong reactions from us is the fatal flaw in human beings. All misinformation is designed in such a way that its novelty factor hooks us. And so you can go on creating a lot of disinformation, and disinformation is winning. These days it's very hard. The old, like if you go back and read the literature, the newspapers also 20, 30 years ago, they had a very measured scientific tone, right? Now you look at it and everything is trying to capture audience and attention. And even the professional newspapers and journals and newscasters, they are trying to be sensational. You know, even weather has become a big thing. Like, you know, all this atmospheric rivers coming along, sometimes there's a huge storm coming and lots of damage will be there. And you go out there and nothing happens, right? Like it barely drizzles, right? But they'll always exaggerate on the side. They will always, you know, err on the side of exaggeration rather than saying that, you know, there is a possibility that it may happen, a smaller possibility, more likely it will be a drizzle. They won't say that. They'll say, so it can happen. Tomorrow can be a big storm, right? Well, anything can happen, isn't it?
That's the farmers and all the insurance companies are doing well because of the insurance.
That's right. That's right. That's right. So people don't distinguish between the possible and the probable. So whenever they hear something, the question is it possible? And if the answer is yes, they believe it. Whereas the question they should ask is, what is more probable? Right? To think in terms of probability is not there in human nature, whereas that is what is needed. Possibility, for example, there could be angels sitting next to me. You just don't see them. And they are giving me all the ideas that I'm talking about. But is it probable? If nothing else, who knows? I mean, I don't think so, but because there's no physical evidence of that. And Occam's razor principle says that it is not necessary to postulate the existence of angels around me. right? Common sense thing is I read the paper and I'm explaining it to you, right? So that's how it goes. I mean, that's the nature of disinformation. Anyway, that's a digression.
So,
What I thought.
like, how is the, since you brought the GAN, how is the GAN related to transformer?
Let's say that GAN was invented in 2014. And actually, one of the co-authors of GAN happens to be my cousin. Yeah, along with all these big guys. So 2014, and it took the world by storm. After that, deep fakes, fake images became. But at that time, the first original GANs were very unstable. They became far more stable with the coming of variational GANs, and then the Wasserstein GANs. And GANs itself have been evolving. Transformers, right, and GANs. Oh goodness. So when you come across, so hold your thought. When you come across these neural architectures, right, and you see how powerful each of these neural architectures are in their own unique way, you'll realize how much the world has changed. Right? So, for example, if you're a developer writing code, forget about it. Yeah, like I think Shanavas was here today. He was saying, I didn't remember that, but he said that 3 or 4 years ago, I had said that the world will be completely different in 5 years. It will be hard to recognize. AI would have eaten the world for lunch. I said it would happen in 5 years. 3 years later, you have no doubt that AI is eating the world for lunch. So change is everywhere. So I don't know. So if you like AI, there is actually a TV show. Okay? And usually I don't watch TV show, but I like the ones that are about science and math and AI. So the 3 TV shows I like. One is Bones.
What is it?
Bones.
Bonds.
Right? It's about it's sort of a fictionalized version of the life of a great forensic anthropologist who was partly, I believe, on the spectrum, perhaps. Yeah. So that I love. You can try it out. The other one is called Numbers. You've seen big fan of Numbers. Yes, absolutely. It's actually about use of machine learning quite a bit. Like each episode, some crime or some mystery is solved using machine learning. Numbers. And the third one that I like is a person of interest. Right. So the person of interest is somebody has created an AGI. Right. But people don't know. So the creator goes about looking at the world and says, the milkman goes doing his job and everybody is doing that. What they don't know is that the world has changed, right? The underlying world has changed. It looks the same, but it isn't the same. It has changed. So, well, that's AI, guys. Anyway, now comes this one little equation that we missed. The only thing that we missed, this equation. So let's look into that. What are we doing? We concatenated the U, V, the embedding vectors, and their difference together to create a long concatenated vector. We want to pass it into softmax to get your voltages, your probabilities, right? But it's just a thing that because right at that moment, you can put one more layer of weights to train on, right? That what linear transformation of this vector should you actually give to softmax instead of giving it the vector itself? Yeah. So it's one extra bit I noticed that they had put in, and it must be for good reason. They must have noticed, right, benefits from it. So how do you discover that you should also multiply? At the back of your mind that you can, these weight matrices, right? They are like peanut butter and jelly, right? So you can keep layering it. You can just put it as sandwich between any layer that you see in your network. Seriously, right? The only question is to put it or not. That's my intuitive picture. And to some extent, the dense layers, fully connected dense, also like that. They're like peanut butter and jelly. Just wherever you just layer it in and see, does it get tastier or is your network doing better? But I mean, obviously, when you do it, you can say, in hindsight, of course, you should have done it. Why lose that degree of freedom? Because if it is not necessary, it will be a diagonal matrix. It will train itself into a diagonal matrix, right? But of course, it won't. So they must have found it useful. So this is it. The only math in this entire paper was this bit, and you know this. And the cosine part makes sense during inference time. Given two vectors, similarity is cosine, of course. Right. So then, of course, you have to see how well it beats the state of the art. And you can see that it does. The S-BERTs, like you notice that if you take, so these are various NLP tasks and corpus or data sets on which you benchmark. And so everywhere, you notice that the biggest number is this. Actually, I should use this is too thick a pen, so I should just say this. Right. So you notice that how many of these are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5. So there are 5 other neural like transformer architectures there, right? Except for one, this one, right in its very first paper, like in its very first version, the sentence BERT beats those models hands down, right? It takes 6 of the gold medals out of the 7.
And what is this SKS 12, 13, 14?
Oh, these are like a text similarity measures, right? Tasks, and they are data sets on which you try it out. Benchmark. So, if you want to compare with somebody, you have to do apples to apples comparison. So you do it on those data sets. So isn't it impressive? Like it takes away, it's just like the BERT paper itself, it came and took away. So there's a bit of history to it. Like when this sentence BERT came out, it took people a little while to realize that what had happened and that what it is doing to search. First, they realized that, goodness, now we can do AI-based meaningful search. Search was still possible using the cross encoder, the BERT itself, but it was horrendously slow and not feasible. Possible is not feasible. Yeah. But this made it feasible. Now you hybridize it with the approximate nearest neighbor algorithm, and it becomes really possible, right? And then you tie it, and then you can say that we can always improve the accuracy in the final stage by bringing in a cross encoder if you want to. Is it being used? You bet. I'm under NDA, I can't talk about it, but let me just say that some of the biggest social media companies are using this, while the rest of you are using Elasticsearch.
So the difference between S-BERT and the S-GoBERT.
Oh, BERT. So what the thing is, you take BERT, right? See, here's the thing.
Because he had it in the beginning, I think.
No. This is it. See here, you made a Siamese network. What are the things? There is a transformer here, followed by pooling, and then the rest of it. Which transformer you used? If you use BERT, it is S-BERT. If you use Roberta, it is S-Roberta. You got the idea, no? That is all it is. No. Because you still have the choice which transformer you'll use. You could use anything. And now people are, so the latest ones actually use different, they're even better ones, right? Now, if you remember that both BERT and those BERT have been trained on certain specific tasks. So when they are trained first on the NLI task, then you say, okay, that large, small, whatever the size is. So if you remove this, now observe, if you forget about in this table, forget about the BERTs, S-BERTs, sentence BERTs. Look at this. The first benchmark puts the universal sentence encoder as big, isn't it? But how much is the difference? There's a 10-point difference in score. Those differences don't just easily come. Because universal sentence encoder, I remember when it would come out, it was considered a big advance on everything. Because if you look at the column, everything is smaller than that by a margin, right? Then if you you look at the next benchmark, once again, universal sentence encoder is doing very well, and the InfoSense glove. So you just use glove embeddings and you find similarity. What was glove embeddings? I told you that before people started doing context-aware embeddings, they were doing just training a neural network, not transformers, no attention, just a deep neural network. take a feed-forward network and train it to produce embeddings, but it's a static embedding. One word will have only one embedding. So it is word meaning. So you could do king minus man plus woman is queen, that sort of thing. So at the level of that, the trouble is words have multiple meanings. Yeah. So glove was one of the better ones, one of the best ones for those static word embeddings. Yeah. And their very nature was that they were context unaware. They were global embeddings. And so if you look at it, for this task, universal sentence encoder was actually not doing much better than just a simple sentence inference using glove, right? Now, here also, this universal sentence encoder is still the state of the art, yeah, for most of those tasks. And this thing dethroned it, sentence bird dethroned it for all tasks except the Sekar. Right. Yes. So it is worth, if you want to explore, find out what the state is today. Yeah, worth knowing where are we, what are those numbers. Yeah. And once again, you notice that if you look at this thing, this column, this column, right, you can clearly see that the winners quite not trained for STS, etc., always the scores are high for these models. I won't go into the specifics of the benchmark. It isn't important.
Why doesn't people in enterprise use this?
See, frankly, right, enterprise, see, well, I'm going to say something controversial. Let me stop recording. So guys, this is sentence bird. I was thinking that today I could do one more architecture. I would do, but instead I'll plant some ideas into your head, right? Some thought questions. The third question is, think about see from words, like you think about how DALI could be done without reading the paper of DALI. How can you convert text into images? Right. So I told you that the other part of the journey is there. Let's say that image, because on the web you can scrape captions from images. Now, so you have some way of convert clip. Clip will convert the clip architecture. We'll do that next time. Will convert an image to text, right? But how will you know? So let's think through some of the steps by which you'll convert a text to an image. You can't reverse it. If you reverse it, so suppose I have a text and all you do is find the closest caption in the embedding space, and then next to it, you find the image, you will only end up regurgitating images that exist, isn't it? From a repository of images. So that becomes nothing but image search using voice prompt, isn't it? And in fact, we saw that. We did that in the sentence word. But now think, and I invite you to think, don't look at the DALI and all of that yet. Invite you to think, up to clip I've given you, up to sentence word, you know the embeddings, some way of creating hidden representations. Whether you use sentence word, you use something else, doesn't matter. Some embeddings. Words can become embeddings, images can become captions, and therefore they can become embeddings. So what do you need to do now? You have a matrix. What can you do? You can project both of them, let's say in a embedding space, all the captions and so forth. So now I can take a text prompt, I can find the images that are sort of where, you know, the neighborhood in the vector space where all of those, you know, the images whose caption embedding are nearby, isn't it? Wherever I go around it, there are some images whose embeddings are nearby. I can pick some of those images. And now what do I need to do? Merge them. Somehow, exactly. Somehow I need to create something now. Merge them I can do with Photoshop, but that's not a good idea because that would be layers. So what I could do, and at this moment, think through some ideas. I'll give you a hint. Imagine you started with Gaussian noise, just noise. How would you know that from noise, right? So let me make it even like this. Suppose this is so imagine a sphere, globe, and you know that your prompt has taken you to this region of the globe, on the surface of the globe. There are all of these images there, but it doesn't matter. Now imagine that noise is at the center. I mean, it's at the core of it because it's not going in any direction, let's say. And you generate an image in the beginning that is just noise. No. So what can you do to the noise, right? That will take you a little bit closer to that region.
Gans.
So what you need to do is you just make small perturbations to the noise, right? And check whether you have gotten the embedding of the noise has in any way come to that neighborhood, closer to the neighborhood, not to any one picture, but closer to the neighborhood. Then you make further perturbations on it and further perturbations on it, right? I mean, these are just ideas. I mean, I'll explain the stability and all these algorithms in detail, but very hand waving some approaches could be, and not very efficient, that you randomly make perturbations, right? And then you keep picking, let's say that as a selection, you pick those perturbations that took you closer. Then you perturbate those perturbations, right? And so it's a process of, like, that's why you use the diffusion in these words. So you keep perturbating till you end up in the neighborhood. But remember, you don't end up on an image because other images are pulling you away. The embedding vectors of other images are pulling you away. So you will take some trajectory and land somewhere, right? Such that you are in that neighborhood. But your picture doesn't look like noise anymore. It has taken shape. You would start doing something, some line, something, or their curves will start forming, isn't it?
So you're merging parts of different neighborhood images and getting what you find.
No. You're taking a random image. You're not looking at this. You're basically saying, let's make a perturbation to this. You do something, right? You put some random structure on it. And you see, have I moved closer to this neighborhood, right? Then you make more perturbations, keep making these perturbations, right? And doing this, and then you come very close to that. And after a little while, your loss function is not going down, right? Because you're basically sitting in the region, in the center of those image embeddings. Whatever this shape looks like, is there any reason to doubt that it is the composite of those things? Right? So now we can evolve this idea.
But we're still living in that latent space.
It is only in the latent embedding space.
Right? But from there, how do you get to the next?
No. See, think about it this way. You take an image. So here is the embedding space. In this embedding space, what you do is you have a text prompt, right? Now, the text prompt has put you here somewhere. You know that around it, let's say that there's a dog sitting upon a table, right? It has put you here. You need to get there. But how do you get there? You have an image, which is complete noise. So your text embedding is here. You do small perturbations of it. You make some random mutation or perturbations on this image. Look at its embedding. Its embedding is not in the center of the sphere. It is zigzag somewhere, right? You say, did it zigzag the other way around or this way, right? If it this way, good, right? It will make some random, just this way. This way means may not be a start point. It may go this way, right? But it's still closer. Then you make some other perturbations to it. It's like, oh, little closer. Let's keep this, right? So what will happen? You don't know where this is. All you know is wherever this is, my distance to this is getting less. Right? You're seeing this. So you are just making perturbations to this image and asking, hey, am I getting there? More. Am I getting there? Right? And suppose you were to keep doing this hand-wavingly. So this is a very hand-waving argument. What do you think will happen? Two things will happen. You will have infinitely many paths to that trajectory. And also when you reach that region, there will be many points that have the same sort of a image, that many images, because you have taken many paths. See, every path is different. And so every path puts a different structure on your image, perturbational image, right? So what is that? Because an image is a composite of all the perturbations, and all the perturbations are different. Cumulative paths are different. Every time you'll come up with a different image. Is it giving you some sense of how it works? No, from text to image. Text to image, the reverse part of it. How are we generating text to image from it? Right. So take this idea now, and obviously I've given a very sort of a hand waving. So I'll tell you something that I learned in grad school. You would read a paper and this theorem, corollary, lemma, right? So then I would talk to a friend, and the friend would say, no, wait a minute. He would give a complete hand waving argument in the air. And you know that is imprecise and so on and so forth. But you know, it has landed you in the right spot. Right? After that, refinements are there. You can make it more precise. When you start reading the paper, it all makes sense. Right? So you should always understand these concepts like that. Start with something, you know, intuitive feel for it. Let it be partially wrong, but then you get it. But you see how you can approach this class of problems. Right? So that makes text to image possible. And you can generate infinitely many images out of a text prompt.
Is it also a form of gradient descent? You kept saying
Oh, yes, yes, yes. It is, you do. I mean, gradient descent for the neural networks is a given, because you create a loss function, which is the distance from here to there, and you gradient descent it. So you will make, but see, sometimes what happens is if you want to keep randomness there, say, first of all, gradient, stochastic gradient descent anyway has randomness, zigzag path built in. But with stable diffusion, there's a little bit more technology to it. There's some deliberation to it, and we'll come to that. Yeah. There's a very good, deep ideas, fun ideas. And that brings us, so you notice, guys, that this time when we are doing NLP, for those of you who didn't know before, I'm focusing a lot on generative AI. Yeah. And in the deep learning course also, it will be very heavily generative AI, because it used to be that machine learning was mostly discriminative machine learning, in the sense that descriptive models are that tell cat versus dog, right? Or inference, or how much revenue will your shop earn next year, number, prediction, regression problems. Those are discriminated. Discriminated means based on certain input data, what is your prediction of the label based on this? But so you find the conditional probability, whereas the generative models from probability theory take a different point of view. They say that including the target space and the inputs, what is the probability distribution? Because if I know the full probability distribution, I can just cherry pick a point from a region and say how probable it is that this is a cat, right? So suppose the probability of its being a cat is very, very low out there, right? Or dog or whatever it is. So now what I can do, I have a full probability map. I can randomly keep sampling it. So I can now generate input data, right? Because I don't need only the data that was there. I can start generating. If I have learned the full probability distribution, hey, there are infinitely many data points I can pick out and say, hey, this is X, this is Y. So in recent years, GAN really made the deepfakes and all this there. So you could see the generative thinking taking off. And after that, recently, generative AI, I mean, it's sort of the buzzword. People don't seem to be, if you say that you do machine learning, they will glaze over it. If you say you do data science, oh, some old stuff, right? If you say I'm doing AI, pass. If you're doing generative AI, 3 VCs are running after you.